Okay, so you sent over a really interesting set of materials on reservoir stimulation.
Yeah,
It seems like this is a really important part of getting oil and gas out of the ground.
it really is.
So we want to kind of take a deep dive into that today,
Great.
and specifically looking at how engineers can kind of enhance the connection
Uh-huh.
between the actual well
Yeah,
and the reservoir itself to really get good production and recovery.
right.
So maybe we could start with the basics, like
Sure.
how is oil and gas actually stored down there?
Well, think of a reservoir like a sponge made of rock.
Okay.
And the rock has all these tiny little spaces interconnected.
Uh-huh.
And that's called porosity.
Okay.
That's where the fluids are.
Okay.
That's represented by the Greek letter phi.
Okay.
Now, the fluids themselves, they're complicated mixtures of
Okay.
hydrocarbon molecules ranging from simple methane
Hmm.
to really heavy, complex molecules.
I see.
Now, crude oil,
Yeah.
which is the liquid hydrocarbon, is often classified as paraffinic or asphaltenic.
Okay, so it's not all the same.
No, not at all.
Down there.
These hydrocarbon mixtures, how they behave under pressure and temperature, is critical to
Right.
understand reservoir performance.
Mm.
And we often simplify it by considering just two phases,
Okay.
gas and oil,
Okay.
and we call those pseudocomponents.
Okay.
Now, when we're talking about pressure, a key thing
Mhm.
is bubble point pressure, or PB.
Okay.
If the reservoir pressure is above the bubble point pressure, then all the hydrocarbons are dissolved in the liquid.
Okay.
So it's a single phase liquid. We call that undersaturated.
Undersaturated. Okay.
But as the reservoir pressure drops below PB,
Right.
then gas starts to come out of solution.
I see.
And you have what's called a saturated reservoir.
Okay.
Now, if you just have gas,
Yeah.
then we talk about dew point pressure.
Okay.
That's kind of the equivalent.
Okay.
But that's only when you just have gas
Right.
in the reservoir.
Now, you mentioned water also being present.
Yes, water is always present.
Uh-huh.
And in fact, the pore space,
Okay.
that's that porosity
Yeah.
that's filled with both hydrocarbons and water.
Yeah.
The water that we can't produce
Right.
is called connate water or interstitial water.
Right.
And we represent that by Stabuban.
Okay.
Now, you can also have separate water zones
Yeah.
underlying the oil or gas zone.
Okay.
But the transition between these
Right.
isn't really a sharp interface.
Right.
There's kind of a transition zone of several feet
Okay.
due to capillary pressure.
Right.
So that's something that's really important to keep in mind,
Uh-huh.
is that during production, you don't want to produce water
Right.
because it's not good for a number of reasons.
And it doesn't really help us either.
Yeah,
Right?
not at all.
Okay, so now we kind of have a picture of how it's down there.
Yeah.
You know, it's not just like this big pool of oil, right?
Right.
It's much more complicated than that. But if we want to actually estimate, how much is there?
Yeah.
How much oil or gas is there initially? How do we even do that?
So we have a basic equation that we use to estimate
Okay.
the initial hydrocarbon volume in place.
Okay.
So that's the area of the reservoir
Okay.
times the net thickness
Uh-huh.
times that porosity, that phi, and
can
then
do that.
times 1 minus the
Okay.
connate water saturation, STOBC.
Okay.
Now that gives us the hydrocarbon volume in place in the reservoir.
Right.
But when we talk about barrels of oil produced,
Yeah.
we measure that at the surface
Right.
at standard conditions.
Okay.
So we have to use conversion factors.
Okay.
And these are called formation volume factors.
Okay.
For oil, that's BO.
Okay.
And for gas, that's BG.
I see. Okay.
So these are used to convert the reservoir volumes to
Uh,
surface volumes.
Okay, so that makes sense because obviously a barrel of oil down there
Yeah.
under all that pressure and temperature is going to be quite a bit different than a barrel of oil at the surface.
Right.
Okay, so we drill a well into the reservoir.
Yeah.
And we have a path for the oil and gas to flow.
Right.
So how does that actually work?
The main thing is when we drill a well,
Yeah.
we're creating a pressure difference.
Okay.
So the reservoir has a higher pressure
Right.
than the wellbore.
Mm-hmm.
And this pressure difference is what drives fluids to flow from the reservoir
Okay.
to the wellbore.
Right.
The greater that pressure difference,
Yeah.
the higher the flow rate.
Okay.
So that's one of the key concepts in production engineering.
Right. So if we could just get the pressure in that wellbore as low as possible,
Yeah.
then we could get a ton of oil out.
That's what we try to do, but there are limits
Right.
to how low we can get that pressure
Yeah.
economically
Right.
and physically.
Okay. And then when we're talking about flow through porous rock,
Yeah.
there's this thing called Darcy's Law, right?
Yes, Darcy's Law. That describes fluid flow
Okay.
in porous media.
Yeah.
And it says that the flow rate, Q, is proportional to the permeability of the rock.
Okay.
That's K.
Right.
And the pressure gradient.
Okay.
And the key takeaway here is that while we can manage the pressure gradient, that permeability of the rock is often fixed.
Right.
So that's why we put a lot of effort into trying to improve the permeability near the wellbore.
Right. So that would be simulation.
That's right.
Okay.
Stimulation techniques.
Okay. And I know there's, I guess, a special version of Darcy's Law that applies to flow around a well, right?
Yes. So around a vertical well, the flow is generally radial.
Okay.
So we adapt Darcy's Law for this radial flow.
Okay.
And that equation in oil field units is Q equals 2 pi KH times the difference between P and PWF, all divided by mu, which is viscosity, times the natural log of Rho over Rho.
Okay.
Now, P is the pressure at the external boundary of the reservoir. Okay. And PWF is the flowing bottom hole pressure at the well. Okay. So this equation allows us to estimate the production rate of a well. And it's really a cornerstone of petroleum engineering.
I see. And the permeability in that equation, is that like a constant value for a given rock?
Well, not exactly.
Right.
So we have to distinguish between what's called absolute permeability and effective permeability.
Okay.
Absolute permeability is when you have a single fluid flowing through the rock.
Right.
That's kind of a theoretical measure.
Okay.
But in the reservoir, you always have at least two fluids.
Right.
You have hydrocarbons and you have water.
Okay.
Now, the presence of a second fluid hinders the flow of the fluid we're interested in. So we need to define something called effective permeability.
Okay.
Which takes into account the fact that there are multiple fluids there.
Right.
And the effective permeability is always lower than the absolute permeability.
So for oil, we would say Co.
Right. Co. For oil.
Okay.
Now, if you have multiple fluids flowing at the same time, then we have to account for what are called relative permeabilities.
Okay.
And these are like CRG for oil, water, and gas.
Okay.
And they describe how easily each fluid can flow in the presence of other fluids.
Right. So they're all kind of competing for space.
That's right. That's right.
To flow through that rock.
Exactly. And those relative permeabilities change depending on the saturation.
Okay.
So the more oil you have, for example, the easier it is for oil to flow and the harder it is for water.
Makes sense.
And gas to flow.
So the more oil there is, the higher the relative permeability of oil.
Right.
Okay. And then you also talked about different ways that a reservoir can flow based on those boundaries and how the pressure is changing?
Yeah. So we have steady state, pseudo-steady state, and infinite acting.
Okay.
Now, steady state is when the pressure at the outer boundary stays constant.
Right.
And pseudo-steady state is when you have a closed outer boundary.
Okay.
And infinite acting is really early in the life of a well when you haven't felt the effects of the boundaries yet.
Okay.
And that's the most complex one to analyze.
I see.
And so we use dimensionless pressure and dimensionless time to look at the initial flow period.
Okay, so there are ways to to analyze that.
There are.
Even though it is quite complicated.
Yes, because the equations are quite complex.
Right. Now, one thing that came up in the material, and you mentioned, was skin effect.
Yes.
And I don't quite understand what that means.
So skin effect is represented by the letter S.
Okay.
And it describes any additional resistance or enhancement to flow near the wellbore.
Okay.
So think of it like a bottleneck or a widening of the flow path.
I see.
Immediately around the well.
Okay.
If it's a positive skin, then there's some damage that's hindering flow.
So there's extra pressure drop.
Right, extra pressure drop.
Okay.
And less production.
Right.
And if you have a negative skin, then that means the permeability in that near wellbore region has actually been improved.
So we've done something to make it flow better.
Right.
Okay.
So stimulation treatments are designed to give you a negative skin to improve the flow.
Right. So if we have a positive skin, you're saying that we'll actually produce less oil than Darcy's law would predict.
Right, because we have to modify
the radial flow equation
right.
to account for skin.
Right.
So the equation becomes Q equals 2 pKh times P minus PWF, all divided by mu, times the natural log of Re over R plus S.
Plus S.
So you can see, if S is positive, that's going to reduce the flow rate, and if S is negative, it's going to increase the flow rate.
Okay, so that makes sense.
Okay.
And that leads us to effective wellbore radius.
Yes.
And productivity index, right?
Exactly. So effective wellbore radius is basically the wellbore radius corrected for skin.
Okay.
And the productivity index is a measure of the well's ability to produce for a given pressure drawdown.
Okay.
Now, mathematically, the productivity index, which is often represented by J, is the flow rate divided by the pressure difference between the average reservoir pressure
and the bottom hole flowing pressure.
Okay.
So in terms of the equation, it's 2 pi kh divided by mu times the natural log of Re over RW plus S.
Plus S, okay.
Now, since engineers can't easily change the kh, which is the permeability thickness product of the reservoir, they focus on maximizing this productivity index by trying to reduce the skin and or reduce the flowing bottom hole pressure.
Okay, and reducing the skin, that's the stimulation.
That's right.
And reducing the flowing bottom hole pressure.
That's often done by artificial lift.
Artificial lift, okay.
Which is a whole nother topic.
Right, which we might talk about in another episode.
We could.
Okay, and then there was this brief mention of units.
Yeah.
Which I found interesting.
So the oil field has its own set of units.
Right, like barrels per day.
Barrels per day. Centipoise.
Okay.
And these units don't always go together neatly. So we often have to use conversion factors in the equations.
Right.
Now, in the material you sent, the convention was to use these oil field units in the equations themselves.
So you'll see things like 141.2, which would normally just be 2 pi.
Exact.
Okay, that makes sense.
So you'll see those constants in the equations.
Okay, so we've got these different flow regimes, right?
Yes.
And we've got these equations for permeability and skin effect and all that. But how do we actually tie that together to figure out how much a well can produce?
So we have a concept called the inflow performance relationship, or IPR.
IPR, okay.
And that describes the relationship between the rate at which a well can produce and the pressure at the bottom of the well while it's flowing.
Right.
That's PWF.
Okay.
And the shape of that IPR curve depends on the reservoir characteristics and the flow regime, whether it's steady state, pseudo-steady state, or transient.
Okay.
So we have different equations for each of those.
Good, so maybe we can go through those one at a time.
Okay, so for steady state flow in an oil well, the IPR equation is Q equals KH times P minus PWF.
Okay.
All divided by 141.2 times mu times BO.
Right, the formation volume factor.
Right.
Times the natural log of Re over RRW plus
SS. And that gives you a straight line if you plot PWF versus Q.
Okay.
The point where that line intersects the PWF axis at zero flow is the external boundary pressure. And the flow rate where it crosses the Q axis at zero PWF is the maximum flow rate. Which is often called the AOFP.
AOFP.
Or absolute open flow potential.
So that's kind of a theoretical maximum.
Right. If you could reduce the flowing bottom hole pressure to zero, which you can't really do.
Right. But that's what that would give us.
That's right.
Okay.
Now, for gas wells, it's a little bit more complicated because the properties of gas change with pressure.
Right.
So we have to account for that. And we often use what's called the real gas pseudo-pressure function to do that.
And so if you plot that for gas, does that give you a straight line as well?
No, generally it's not a straight line for gas or for two-phase flow.
Okay, so two-phase flow is when we have
oil and gas together.
Right, okay.
So those are generally non-linear curves, but they still describe the relationship between flow rate and bottom hole pressure.
Right.
And one thing that was really interesting to see was in one of the examples you sent, where they plotted the IPR curves for different skin values. And it showed how dramatic the effect of skin can be.
Right. Even a negative skin
Yeah.
can make a huge difference.
Huge difference, exactly.
Okay.
So even a small improvement in skin
Right.
can lead to a big increase in production.
Yeah, that was really cool to see that.
Yeah.
Okay, and then we have pseudo-steady state.
Right.
So how does the IPR change in that flow regime?
So the equation for pseudo-steady state flow for oil is similar to the steady state equation.
Okay.
But instead of using P, we use P bar.
P bar.
Because the average reservoir pressure and that average pressure declines as we produce from the reservoir.
Right.
So we need to use material balance calculations to keep track of that.
Right. So that average pressure is constantly changing as we're producing.
Exactly.
And how does that affect the IPR curve?
So for a given skin,
Yeah.
the productivity index stays constant during pseudo-steady state.
Even though the average pressure is declining?
Even though the average pressure is declining.
Okay.
So if you plot the IPR curves for different average reservoir pressures, you'll see a family of parallel lines because the productivity index is constant.
So even though the average pressure is going down, the well's ability to produce per unit of drawdown is the same.
Right.
Okay, that's interesting.
Yeah.
And then the last flow regime is transient flow.
Yeah.
And that's the one that you said was the most complicated.
It is. So transient or infinite acting flow occurs early in the life of a well before the pressure transients have reached the boundaries.
Right.
Now, the flow behavior during this period is described by a partial differential equation called the convection diffusion equation.
Right.
And that's a mouthful.
Yeah.
But to analyze it, we use dimensionless pressure and dimensionless time.
Okay.
And if you convert that back to real units, you get an IPR equation.
Okay.
That looks like this. Q equals KH times the initial pressure. Okay.
Minus the flowing bottom hole pressure.
Okay.
All divided by 162.6 times mu times bow.
Okay.
Times the log of time minus 3.23 plus 0.87s.
Plus 0.87s, okay.
The time in that equation is in hours.
Okay.
And if you plot IPR curves at different times during transient flow, you'll see that the flow rate at a constant bottom hole pressure actually decreases over time.
Okay.
And that's because the pressure support from the reservoir is declining.
Right. But it's important to remember that that infinite acting period doesn't last forever.
No, it's temporary.
Right.
Eventually, the pressure transients will hit the boundaries, and then we'll transition to pseudo-steady state.
Okay.
So that's really just the initial flow period.
I see, okay.
That we're looking at there.
So we've been talking about vertical wells.
Yes.
But horizontal wells.
Have become really important in the industry, right.
They have.
So how does all of this apply to horizontal wells?
So horizontal wells have become really important since the mid-1980s. And now they're expected to make up 50% or more of hydrocarbon production. Okay. So we need to be able to analyze those as well.
Right.
So for steady state production from a horizontal well, we use different models.
Okay.
Like the Joshi model.
Okay.
Which was augmented by Economides and others.
Okay.
And that model takes into account the horizontal well length.
Okay.
And the permeability in the horizontal direction, KH, and the difference between horizontal and vertical permeability, which is called anisotropy.
Okay.
So we have to account for all of that when we're looking at horizontal wells.
So we can calculate an IPR for a horizontal well.
Yes.
Just like we did for a vertical well.
That's right.
And I guess then we could compare them.
Yeah.
To see which one is going to be better.
Right. So in general, horizontal wells are more attractive in thick reservoirs.
Okay.
Particularly those with a higher permeability in the vertical direction.
I see.
But they can also offer benefits in thinner formations, even with low vertical permeability, because they increase the contact area with the reservoir.
So it's all about maximizing that contact.
Right. And there's also skin effects that can be incorporated into the horizontal well deliverability equations.
Okay. And just like with the vertical well, you can also adapt this for gas and two-phase flow.
That's right.
Okay.
We can make those modifications.
And then what about pseudo-steady state?
Yeah, so Economides also developed a generalized pseudo-steady state model for horizontal wells.
Right.
Now, that model considers the well's position, both horizontally and vertically, in the reservoir, and it defines something called the Generalized Productivity Index, which we talked about before.
Yeah.
And it also uses a dimensionless pressure that incorporates a shape factor and a vertical effects skin.
Okay, so we're still dealing with skin.
Yes.
Even in these horizontal wells.
Even in horizontal wells.
Okay.
Now, there's also something called vertical eccentricity skin, which accounts for the fact that the well may not be located at the vertical midpoint of the reservoir.
Okay, so we can actually quantify that.
Yes, there are charts and equations that allow us to calculate these skin effects.
Okay.
And there was an example that showed that in an isotropic reservoir...
Isotropic meaning?
Meaning that the permeability is the same in all directions.
Okay.
A horizontal well can achieve a much higher productivity index than a vertical well.
Okay, so sometimes it really makes sense to drill horizontally.
It does.
Okay, now you mentioned earlier this permeability anisotropy.
Yes.
And so... I guess that can have an impact on horizontal well production.
It can. So we often simplify by treating permeability as a single value, but it's really a directional property.
Okay, so today we are going deep, literally, to uncover how we understand what's going on in oil and gas reservoirs. We've got some really cool stuff to dig into, including insights from formation characterization, and reservoir testing.
Lots of great stuff to explore.
Yeah. Basically, this deep dive is all about deciphering those signals, those pressure changes we get from deep underground. It's kind of like unlocking the secrets hidden way down there.
Absolutely. For anyone who's ever wondered how we get access to these resources, or even folks in the industry looking for a refresher, this look at well and reservoir testing will be super valuable. It's really all about interpreting those pressure clues in, the subtle changes to paint a picture of what's going on down below.
Right, and the way we've done that, interpreted those pressure clues, has evolved dramatically over the years.
Yeah.
Our sources point out three big, I guess you could call them breakthroughs or milestones. First, we'll look at semi-algorithmic straight-line analysis, which a lot of people just call Horner analysis.
Right.
Then, the log-log diagnostic plot, which offered a whole new visual way to look at things. And finally, the development of the log-based pressure derivative, which, from what I understand, really, really sharpened our ability to diagnose what's happening down there.
Yeah, these weren't just small tweaks. These were game changers, really foundational shifts that enabled us to pull out more information, richer and more reliable information about a reservoir. Each step built on the one before it, helping us determine things like how easily fluids can flow through the rock, if there are fractures, and even where the reservoir boundaries might be.
Okay, so let's jump right into that first big leap forward, the Horner analysis. Back in 1951, a guy named, Horner, he came up with this, and it quickly became the go-to method, especially for analyzing buildup tests. That's when you shut in a well and see how the pressure changes.
Yeah, and what's so smart about Horner's method is that it basically uses a mathematical trick, the principle of superposition, to understand how the pressure redistributes itself when a well, which has been flowing, is suddenly stopped. Think about those pressure waves spreading out from the well while it's producing. Horner's method lets us analyze how those waves settle down once things go quiet.
Gotcha. And right at the core of this is an equation. It's equation 2-1 in our material.
Yeah.
And, it can look kind of intimidating at first glance. It's got all these variables. Initial reservoir pressure, pi, flow rate Q, formation volume factor, B, fluid viscosity, permeability, K, reservoir thickness, H, producing time, TP, and shut-in time.
Yeah, lots to juggle.
It's a lot. But the cool thing about the Horner plot is how it actually simplifies all of that. So if you take the logarithm of TP plus 8 divided by 8 and plot that on the x-axis against the shut-in pressure on the agas, what you should see is a straight line.
That's right.
Assuming you have what's it called, infinite acting radial flow?
Exactly. Infinite acting radial flow. This means the pressure disturbance spreads out uniformly in all directions as if the reservoir had no limits.
Yeah.
And you can actually see this in figure 2-1.
So it's assuming a kind of idealized reservoir, at least in that sense.
Right, to begin with.
Okay. And that straight line, it's not just a pretty picture, right? The slope of that line, which is defined in equation 2-2, holds the key to some really important information. It lets us figure out the permeability, basically how easily fluids can move through the rock or the permeability thickness product if we don't know the exact thickness of the reservoir.
Exactly.
So a steeper line on the Horner plot would mean lower permeability, right? The fluids are having a harder time flowing.
Exactly. Now, here's the thing, though. If you look closely at Figure 2.1, you'll see that real-world data is rarely perfectly straight.
Of course, yeah.
You could potentially draw several different straight lines through those data points. And this raises a big question: which line is the correct one?
Right. How do you choose?
That was actually a major reason why later techniques were developed. So although Horner analysis gave us a crucial first step in understanding permeability, the fact that it relied on finding this perfect straight line kind of hinted at the complexities that we hadn't quite figured out yet.
Okay, I see. Our sources also mentioned that the Horner analysis can be used to calculate something called the skin effect using equation 2.3. Now, skin in this context, it sounds a little odd. What exactly does that tell us?
Think of skin effect as a way to quantify any damage to the permeability or any improvement right around the well bore itself.
Okay.
You know, drilling and completion processes, they can sometimes clog up those pores in the rock, reduce the permeability near the well bore. That's what we call positive skin. But then other techniques, like acidizing, can actually clean out that near wellbore area, boost the permeability. That would be negative skin.
Got it. So it's measuring how the wellbore itself impacts the flow.
Exactly. And the equation for skin uses that slope from the Horner plot we just talked about, plus the flowing pressure right before shut-in, PWF, porosity, that's how much space there is for fluids in the rock.
Right.
Then you've got the total compressibility of the fluids in the rock itself, the wellbore radius, RW, and a constant to make sure the units all work out.
Makes sense. Now, the material also has equations for drawdown tests, which is when the well is actually flowing. There's equation 2 for the pressure behavior and equation 2.5 for the skin effect in a drawdown scenario.
Yeah.
But the source points out that buildup tests are generally preferred. They're seen as more reliable. Why is that?
Well, there are two main reasons. First, both the Horner analysis and drawdown analysis, ideally, they assume a perfectly constant flow rate, Q.
Okay.
Now, maintaining a rock-steady flow rate during a drawdown test out in the field, that can be really tricky. But during a buildup test, well, once you shut that well in, the flow rate is 0 and it stays there. Much easier to achieve.
That's true. A clean, clear stop.
Yeah. And even if the flow rate wasn't perfectly constant before the shut-in, we can use this concept called equivalent production time, TP, which is defined in equation 2.6. This uses the total amount of fluid produced and the last recorded flow rate. It'll have to give us a kind of effective average production time for the analysis. It's like smoothing out the bumps in the production history.
Okay, that makes sense.
Right. Much more accurate.
Yeah, clean stop is definitely easier to get than perfectly steady flow.
Right.
What's the second reason for favoring buildup tests?
Yes. The initial reservoir pressure, pi, which you absolutely need for analyzing drawdown data, is often not known precisely, especially if it's a new reservoir.
That makes sense.
Buildup analysis has a real advantage here.
Yeah.
It doesn't actually require you to know pi up front. In fact, if you extend that straight line on the Horner plot all the way to where PP plus A divided by E equals 1, that basically means infinite shut-in time, then the pressure value where that line intercepts the axis actually gives you an estimate of the initial reservoir pressure. It's quite clever.
Wow, that's really useful. So Horner analysis was a huge step forward. It gave us these tools to estimate permeability, skin effect, even the initial reservoir pressure. But as we saw back in Figure 2.1, pinpointing that one true straight line, that could be tricky. Which leads us to the next big advancement. The log-lag diagnostic plot.
Right, because researchers recognized that relying just on those semilog plots had its limitations. People like H.J. Ramey and his colleagues, they really pioneered using log plots as a way to better understand, diagnose what the pressure was telling us during a well test. That 1970 paper by Agarwal and his co-authors, that was a landmark moment in this field.
For sure. Figure 2.2 in our source material shows some typical pressure response patterns on a log-log plot.
Yeah.
And it looks pretty different from those straight lines we saw on the Horner plot.
Yeah.
What exactly are we looking at here?
Okay, so on a log-log plot, we're still plotting pressure change or pressure difference against time.
Okay.
But here's the key. Both axes are now using a logarithmic scale.
Okay.
That allows us to see a much wider range of pressure and time values all on one plot. But even more important, different flow regimes, different ways the fluids are moving within the reservoir, they create characteristic shapes or slopes on this log-log plot.
So the shape itself tells a story.
Exactly. For instance, early-time wellbore storage effects, where the pressure response is dominated by the fluid compressing or expanding inside the wellbore itself before the reservoir really starts to react.
Okay, yeah.
That shows up as a straight line with a slope of we call it a unit slope on the log plot. Imagine squeezing a balloon. That initial pressure change you feel is mainly the balloon itself squeezing the air inside, not the air escaping.
Right, I get it. So that early behavior has a very distinct fingerprint on the plot.
Exactly.
Now, figure 2.2 shows two sets of curves, one for downhole buildup and one for surface buildup drawdown. What's the main difference between those two scenarios?
So downhole shut-in means you're closing the well very near the reservoir, minimizing the volume of fluid trapped within the wellbore.
Okay.
This drastically reduces those early-time wellbore slippage effects. Surface shut-in or drawdown tests, where you're closing or opening the well at the surface, well, you've got a much larger volume of fluid in the wellbore, which leads to more noticeable and longer-lasting wellbore storage effects, which can actually mask what the reservoir itself is doing.
Oh, so it makes it harder to separate the well's response from the reservoir's response.
Precisely.
Okay. Our source mentions equation 2.7, which describes the mathematical relationship during this wellbore storage period. It links dimensionless pressure, PD, and dimensionless time, TD, using something called the dimensionless wellbore storage coefficient, CD. Now, I know the term dimensionless might sound a bit abstract, but what's the takeaway message here?
The key here is that this early-time wellbore storage behavior has a distinct signature, that unit slope on the log-log plot.
Gotcha.
And by using dimensionless values, we can actually compare results from different wells and reservoirs, regardless of their specific units or scales. It's like putting everything on a level playing field for comparison.
Okay, that's super useful. And Agarwal et al., they actually came up with a really handy rule of thumb. They said that on a log-log plot, the end of this dominant wellbore storage period would typically be about 1.5 log cycles of time away from the start of that ideal infinite-acting radial flow. So this gave analysts a rough guide as to when they could probably switch over to the Horner semi-log analysis and be more confident about those straight lines.
Right, a very practical guideline.
Yeah. So the analytical process evolved, right? First, you'd use the log-log plot to get axial diagnosis, figure out what flow regimes are present, identify when that radial flow period seems to be starting, and then you could apply the Horner plot to actually calculate your permeability and skin effect. It was a two-step detective process, much more sophisticated than just jumping straight to the semi-log plot.
It was, but it wasn't perfect. The log-log plot of pressure difference versus time still had limitations. Our sources point out three main ones. First, tests, especially in those reservoirs with low permeability, where the pressure changes happen slowly, they're often just not long enough to fully reach that textbook infinite acting radial flow behavior.
Okay.
This means that the Horner analysis, which really depends on that fully developed radial flow, can still be shaky.
Right. You need enough data points within that straight line region on the Horner plot for it to be reliable.
Exactly.
What was the second challenge with that log-log plot?
Well, a reservoir can have other complexities, like natural fractures or dual porosity systems. That's where you have two different types of pore spaces in the rock with different storage and flow properties. These can really mess with the pressure response, making it deviate from that ideal, simple, uniform reservoir. So even if the test seems long enough based just on the log-log plot, using the standard Horner analysis might not be appropriate. Imagine trying to listen to a clear melody when there are other instruments playing out of tune in the background.
Right, it's distorting the signal you're trying to analyze.
Exactly.
And then the third problem, and maybe the most frustrating for those trying to interpret these tests, is the issue of uniqueness, or rather, the lack of it.
Yes, exactly. Sometimes different underlying reservoir characteristics, different things happening down there, they could produce pressure responses that look almost identical on a basic log-log plot, especially if the well test was short. So you might see a certain shape, but it could be caused by 2 or 3 different things happening in the subsurface. It's hard to be absolutely sure about what's really going on.
Yeah, that would make things really tough. Our sources mention type curve matching, which is where you basically overlay your field data onto these pre-calculated curves that represent different theoretical reservoir models. But they point out that this method also has its limitations. Particularly, it's not always sensitive enough to pick up on subtle changes in the pressure data.
Right.
So all of this really sets the stage for the third major breakthrough, the pressure derivative.
It does. The pressure derivative, that's a powerful tool. It was specifically developed to overcome a lot of those limitations we've been talking about, the shortcomings of both the traditional semi-log and basic log-log analyses. It basically added this whole new level of detail to our subsurface investigations.
Okay, so let's dive into this pressure derivative thing.
Oh.
Equation 2-8 introduces something called the dimensionless pressure derivative, PD, with respect to the natural logarithm of dimensionless time, PD. Sure. That's a pretty technical description. Why is this particular form of the derivative so important?
Well, it turns out that this specific way of calculating the derivative, which was presented by Bourdais and his colleagues in 1983, it was incredibly revealing. Figure 2.3 actually shows the complete set of type curves for an infinite acting reservoir, and now it includes this new pressure derivative curve right alongside the pressure curve. The key here is that the derivative acts like an amplifier, highlighting features in the pressure response that might be too subtle to spot clearly in the pressure data itself. So it makes them much easier to pick out, to recognize, to diagnose. Think of it like using a microscope to see tiny details you'd never see with the naked eye.
Okay, so it brings those hitter details into focus.
Precisely.
So how does this derivative behave during that early time wellbore storage period we discussed?
Just like the dimensionless pressure itself, the dimensionless derivative will also show a unit slope, that straight line with a slope of 1, on a log-log plot during wellbore storage. That's shown in equation 2-9.
Okay.
So in those very early moments of the test, both the pressure and its derivative basically follow the same upward trend.
Got it. They're moving in sync. What happens to the derivative as the test goes on and we transition into that crucial radial flow period?
That's where things get interesting. During the radial flow period, when that semi-log approximation starts to become valid and you'd expect to see a straight line on a Horner plot, the dimensionless derivative approaches a constant value of 0.5.
Okay.
This is described by equation 210.
Got it.
And on the log-log plot, that means you see a nice flat horizontal line. It's a clear, distinct indicator that you've hit that key radial flow regime, the one you want to analyze to get your permeability.
Right, so that flat line on the derivative plot is a good sign. Our source then gives a more general relationship between pressure, PD, acting as a power law of time, basically TD raised to the power of M, and its derivative.
Yes.
It's the equation 212.
Yeah.
And it points out specific values of M for different flow regimes, 1.0 for wellbore storage, 0.5 for linear flow, which is like the flow into a fracture, and 0.25 for bilinear flow, an even more restricted type of flow into a fracture. What's the practical use of knowing this?
Well, this is where the diagnostic power of the derivative really comes in. On a log-log plot, the pressure curve and its derivative curve, they appear as parallel lines. And the vertical distance between those lines is directly related to that value of M.
Okay.
This parallel behavior, with that specific vertical offset, it's an incredibly valuable signature.
Okay.
So if you see two parallel lines with a vertical separation that corresponds to M and 0.5, that's a strong indication that you're observing linear flow. It's like having a set of matching fingerprints that confirm the type of flow happening in the reservoir.
I like that analogy, the fingerprint of the flow. So the pressure derivative gives us a much more rigorous way to check our interpretation.
Absolutely.
It's not just the pressure curve itself that needs to match some theoretical model. Its derivative also has to match the predicted behavior. It's like getting a second opinion, a more sensitive one, on what's happening down there.
Exactly. You see, the trends in the pressure data during the middle and late times of a well test, they can sometimes be ambiguous. You might have a few different reservoir scenarios that could explain what you're seeing, but the pressure derivative, it often shows much more distinctive behavior during these periods.
So it helps to differentiate between those different possibilities.
Yeah.
Now, when we talk about early, middle, and late time in well testing, what are we actually referring to?
That's a good question. Generally, we're talking about when different flow phenomena tend to dominate the pressure response. Early time is usually all about wellbore storage effects. Then, as the test goes on, the middle time might reveal the influence of fractures or other heterogeneities within the reservoir. And then finally, late time is when we start to see the effects of those reservoir boundaries.
Okay, so it's a progression of different influences over time.
Exactly.
Now, our source mentions that a lot of well test analysts rely heavily on those log plots that show both the pressure and its derivative together to diagnose the reservoir model. But to do this, we need to actually calculate the derivative of the pressure data that we collect from the well. How do we typically do that?
Well, there are several different algorithms and software programs that can do this.
Okay.
The simplest approach is to look at small segments of the pressure data over short time intervals and basically calculate the rate of change of pressure with respect to the logarithm of time.
Okay.
More advanced methods use smoothing and filtering techniques to minimize noise in the data so you get a more accurate, stable derivative.
So it's about refining the calculation to make it as accurate as possible.
Precisely.
Figure 2.4 shows some really helpful examples of these combined pressure and pressure derivative log plots for a bunch of common reservoir systems. You can clearly see that additional line representing the derivative. It also mentions that for buildup tests, those pressure responses are often calculated using superposition, and then the derivatives are plotted against Horner time, which is a specific time function used in buildup analysis.
Right.
Let's walk through a few of these examples to see how the pressure derivative can help us diagnose what's going on. Example A is a homogeneous reservoir, a simple, uniform one, with both well-bore storage and skin effect. What clues does the derivative give us in this case?
So in example A, what you typically see is a hump in the derivative curve at early times.
Okay.
And that hump is a direct result of those well-bore storage effects. Then, as the test progresses and you get into the radial flow period, the derivative flattens out, approaching a constant value of 0.5 on a dimensionless plot, or you'd see a flat region on a Horner derivative plot.
Okay.
This flat section on the derivative plot, it lines up exactly with the straight line you'd analyze on a Horner semilog plot to determine permeability in skin.
Got it. So that flat line in the derivative confirms that you're in that radial flow regime.
Absolutely.
Example B shows a well that only partially penetrates the reservoir thickness. What does the derivative look like in that situation?
Well, with partial penetration, after that initial well-bore storage hump in the derivative, you often see a sort of plateau or near plateau region.
Okay.
That tells us that you're seeing radial flow, but it's only happening through that limited portion of the reservoir that the well is open to.
Right, only through the section that's actually exposed.
Exactly. Then, as the pressure disturbance spreads out further and the full reservoir thickness starts to affect the pressure response, the derivative will usually drop down to a lower plateau.
Okay.
The source also mentions that to really see these partial penetration effects clearly, it often helps to shut in the well downhole closer to the reservoir, or to use more advanced analysis techniques like deconvolution.
Got it. So the derivative helps to identify those subtle effects of partial penetration.
Exactly.
Example C and D focus on vertical fractures connected to the well, showing both linear and bilinear flow. How does the pressure derivative help us diagnose those situations?
Okay, so in both linear and bilinear flow towards a fracture, the pressure change and its derivative on the log-log plot, they'll both show up as parallel straight lines.
Correct.
For linear flow, which would have a half slope on a pressure versus time log-log plot, the vertical distance between the pressure and derivative curves, that corresponds to an M value of 0.5.
Got it.
For bilinear flow, which has a quarter slope on the pressure plot, the M value is 0.25, and you'll see a different vertical separation between the lines.
Okay.
The source also points out that there are special plots, such as pressure versus the square root of shut-in time for linear flow, or pressure versus the fourth root of shut-in time for bilinear flow, that can be used to determine things like fracture length and conductivity from the slopes of those lines.
So the derivative, combined with these specialized plots, gives us even more detailed information about those fractures.
Exactly.
Example E shows what happens when you have sealing fault nearby. What does the pressure derivative tell us in this case?
Well, a sealing fault acts as a barrier for flow, essentially making that pressure disturbance bounce back.
Okay.
And what you typically see is that the derivative plateau level, it doubles compared to what you'd see in a reservoir without a fault. That doubling of the derivative is a really strong indicator of a sealing boundary. And on the traditional Horner plot, this shows up as that characteristic doubling of the slope at later times.
Right. The derivative makes that boundary effect much more apparent.
Absolutely.
Example F illustrates a well that's in a closed drainage volume, basically a reservoir that's not getting any fluid influx from the surrounding formations. How does the buildup pressure derivative behave in this case?
This one's interesting. So in a drawdown test in a closed reservoir, you'd see a unit slope in the pressure data at late times.
Okay.
But in a buildup test in that same type of reservoir, the pressure derivative will actually drop towards zero at late times.
Huh. Okay, so the behavior flips between drawdown and buildup.
It does. And that distinct difference in the derivative, it helps us tell the difference between the effects of closed boundaries from other types of late time pressure responses.
Got it. So The derivative helps us distinguish between those scenarios.
Exactly.
Okay, example G deals with a channel-shaped reservoir. What happens there?
Right. So in a reservoir that's long and narrow, like a channel, both the pressure and its derivative, they tend to show this parallel behavior with a slope of a half on the log-log plot, but this happens at late times.
Okay.
And again, there are those specialized analysis techniques like plotting pressure versus the square root of time, which in this case can be proportional to the square of the channel width. That allows us to estimate the dimensions of the channel.
So once again, the derivative, combined with the right analysis, unlocks more information about the reservoir's shape.
Exactly.
Finally, example H shows us the classic signs of a dual porosity reservoir. What should we look for in the derivative here?
Dual porosity systems, with their connected networks of matrix blocks and fractures, they often have a very characteristic dip or valley in the pressure derivative curve.
Okay.
This valley is caused by what we call interporosity flow, which is the transfer of fluid from those less permeable matrix blocks into the more permeable fracture network.
Got it.
The depth, shape, and timing of this valley in the derivative, they can give us valuable clues about the storage and flow properties of both the matrix and the fractures.
Wow. So we can really learn a lot about the interplay between those two systems.
Exactly.
Going through all these examples in Figure 2.4 just shows how much more information we can get about a reservoir by analyzing the pressure derivative along with the pressure data itself. It really does paint a much clearer, more detailed picture of what's happening underground.
It does. And the log format, especially when you use those square log cycles on the axis, it's particularly useful because these patterns, these transient patterns, they have this consistent visual appearance regardless of the specific pressures and timescales involved. It makes recognizing those patterns much more intuitive and reliable. You don't need to keep tweaking the vertical scale of the plot like you sometimes have to do with semi-log plots to see those subtle but important shifts in behavior.
But the source also makes a really crucial point. There are times when the derivative patterns can look quite similar for different reservoir models.
Right.
For instance, the response from a sealing fault might resemble the interporosity flow signature in a dual porosity system, or a closed boundary might look kind of like a constant pressure boundary, and even a dual porosity reservoir might sometimes get confused with a layered reservoir. So we can't just rely on the derivative alone, can we?
You are absolutely correct. While the pressure derivative is incredibly powerful, it's just one piece of the puzzle.
Right.
For a reliable, solid interpretation, we've got to combine that derivative analysis with all the other data we have. That includes the geological information about the rock formations, data from seismic surveys, which give us this big picture view of the subsurface structure, and of course, core samples from the reservoir rock.
So it's about integrating all the clues, building a comprehensive picture.
Exactly. It's like detective work, putting all the pieces together.
I like that. Now, the source wraps up by highlighting a really practical use for pressure derivative diagnosis, and that's using it at the well site during the test itself. How does having that real-time analysis benefit the engineers running the test?
It's huge. Having those pressure and derivative plots updating in real time, it gives the engineers these incredible insights right there on the spot.
Okay.
They can quickly figure out if they've gathered enough data to clearly define that all-important infinite acting radial flow period.
Okay.
So if the main goal is just to determine permeability in skin, they can often stop the test once they see that nice flat region on the derivative plot. That can save a lot of time and money.
Makes sense.
But if the pressure and derivatives start to suggest there might be some reservoir heterogeneities or boundary effects at play, the engineer can make the call to extend the test to make sure they get the full pressure and derivative response.
So it gives them the flexibility to adapt based on what the data is showing.
Exactly. It's about making smart decisions based on the actual reservoir behavior as it's happening.
Really cool. So we've come a long way from those early days of just trying to draw a straight line on a semi-log plot. Now we're using these sophisticated diagnostic plots with pressure derivatives, giving us a much richer understanding of what's happening thousands of feet underground.
Absolutely. Those three major breakthroughs, Horner semi-log analysis, log-log diagnostic plots, and the pressure derivative, they have really transformed the way we understand reservoirs.
For sure.
They've enabled us to move from those basic interpretations to much more detailed and accurate characterizations of these complex subsurface systems. And remember, these systems, they hold incredibly vital energy resources.
They do. And this enhanced ability we now have to diagnose and interpret even those tiny pressure changes, it has big implications for the whole energy industry. It means we can manage resources more efficiently, make better decisions about where to drill, how to complete those wells, and ultimately, we end up with a much more complete and trustworthy understanding of the reservoirs that we rely on.
Absolutely.
Really makes you think about all the research and development that's going on right now in well testing technology and where it might lead us in the future.
For sure. I mean, it's a field that's constantly evolving. There's always something new to learn, always more to explore.
Yeah, that's what makes it so fascinating. Well, on that note, I think we'll wrap things up here. Thanks for joining me on this deep dive into well and reservoir testing.
My pleasure.
Until next time, keep exploring. We walk around on the Earth all the time, and we just sort of take for granted what's under our feet.
Yeah.
And as we've been learning, I mean, especially as we get into oil and gas, what's happening under the Earth is hugely important to how we're able to get those resources out.
Absolutely.
You know, and it's fascinating to me the more I learn about how much is going on down there that we never see.
Yeah.
You know, and one thing that kind of blew my mind was learning that sometimes when we go to stimulate reservoirs, we actually end up producing less, or we have these catastrophic failures that happen way deep underground. And so today what I really want to dig into is all the forces that are at play that are affecting how these rocks behave.
That sounds great.
You know, it seems like it all comes down to rock mechanics.
It does.
Which, you know, before all this research, I'd never even really heard of.
So, I mean, what is rock mechanics?
So rock mechanics, it's kind of what it sounds like. You know, it's about how rocks
behave mechanically. And it's defined, actually, by the National Academy of Sciences as the theoretical and applied science of the mechanical behavior of rock. It is that branch of mechanics concerned with the response of the rock to the force fields of its physical environment.
Wow.
And it's a pretty new field, actually, in the, new-ish, I guess you would say, to the oil and gas industry. But it's so crucial, to understand that, because rocks aren't just sitting there, they're responding to their environment.
Right, because for a long time, I guess, they thought about it almost like everything's just kind of under the same pressure. Everything's all balanced.
Right. They assumed a uniform state of stress, which we call isostatic.
Yeah.
And, we realize now that that's not really the case.
Right.
And it wasn't until we started drilling deeper and deeper that we realized this. We had all kinds of problems. You mentioned catastrophic failures.
Right.
Well bores collapsing, casing failing, all kinds of things that just didn't make sense.
Yeah, you'd think it would be stronger the deeper
you would think
you go, but that's not how it works.
Yeah. So we realized we need to learn more about how rocks really behave. And so mining engineers, actually, they were ahead of the curve. They were dealing with rock mechanics for years and years.
Well, that makes sense, yeah.
And we started realizing that rocks are not inert. They're actually reacting to everything going on around them.
Yeah.
And so that brings us to today, where we have all these techniques for stimulating reservoirs, like hydraulic fracturing. And, it's really important to understand rock mechanics to do that effectively.
Okay, yeah. I mean, it seems like that makes sense, and that's what I'm hoping to really dig into today is like, how do we figure this out? Like, how do we characterize a formation and understand what's going to happen with it?
Yeah, and how do we use that knowledge to do things like stimulate it effectively and, extract oil and gas? So that brings us to this idea of formation characterization through rock mechanics.
Okay.
And it's really about figuring out the mechanical properties of the rock. How strong is it? How does it deform under stress? How does it fracture?
Right.
Those are all things we need to know.
And so, as I was reading through the material, it's clear that there are some folks that have really contributed a lot to this field.
Yeah.
And I guess one that really kind of stood out to me was Hubbard and Willis.
Oh, yeah.
Who did a lot of foundational work, especially with hydraulic fracturing.
Yeah, they did a lot of important work on the mechanics of hydraulic fracturing, going all the way back to like 1957.
Wow, yeah.
And one of the things that they realized was that the stress underground, it's not uniform like we thought, right?
Right.
There are these differences between the vertical stress, which is caused by the weight of the rock above.
The overburden.
Right, the overburden and the horizontal stresses.
Wow.
And this difference is what really drives how rocks break and how hydraulic fractures propagate.
Okay.
So in areas that are like tectonically relaxed, where the Earth's crust is kind of stretching apart, the minimum stress is usually horizontal.
Okay.
So what that means is if you do hydraulic fracturing there, you're going to get mostly vertical fractures.
Okay.
And the pressure you need to pump the fluid in is going to be less than the overburden pressure.
Got it.
But then in areas where there's active tectonic compression, where the Earth's crust is being squeezed together, the minimum stress becomes vertical.
Okay.
So in those areas, you're going to get horizontal fractures, and you're going to need to pump at a higher pressure equal to or even greater than the overburden pressure.
To overcome that.
Right.
Okay, so it really all depends on the forces that are at play in a particular area.
Exactly.
So, I was really fascinated by this sandbox experiment.
Oh, yeah.
That they used to demonstrate
Yeah,
this.
they were really cool.
Yeah, it's such a simple thing, but it's so visual, right? You can just see it.
Totally.
So they just had this box with sand.
Yeah, just regular sand.
And a partition in the middle.
Uh-huh.
And they were even able to kind of track how the sand was moving by putting these plaster of Paris lines in there.
Yeah, that was just to visualize it.
Okay.
It didn't really affect the mechanics of the experiment, but it helped them see what was happening.
Got it.
So they could move this partition and create these different stress states in the sand.
Okay.
And what they saw was that depending on how they moved the partition, they could create either normal faults, where the sand kind of slid down, or thrust faults, where the sand was pushed up and over.
Okay, so one side of the partition would be sliding down, the other would be going up.
Right, exactly.
Okay.
And the angles were different, too.
Oh.
The normal faults had steeper angles, like 60 degrees.
Okay.
And the thrust faults had shallower angles, like 30 degrees. So it really showed how the stress state controlled what kind of faults formed.
Got it.
And they linked this to the principal stresses.
Okay.
The maximum, intermediate, the minimum stresses.
Okay, so now we're starting to get into some of this terminology.
Right.
Like, what is a principal stress?
Yeah, so a principal stress is basically the maximum or minimum stress acting on a point in a particular direction.
Okay.
And there are always three principal stresses. We call them sigma 1, sigma 2, and sigma 3.
Okay.
And sigma 1 is always the largest, and sigma 3 is always the smallest.
Okay, so it's kind of like if you were looking at a box and you're seeing which way is the longest, the shortest, and then that middle side.
Yeah, that's a good way to think about it. In 3 dimensions, though.
Right.
Because rocks are in 3 dimensions.
Right.
So what Hubbard and Willis showed was that in that sandbox experiment, the principal stresses were oriented differently depending on whether you were looking at a normal fault or a thrust fault. So for normal faults, the minimum principal stress was horizontal.
Okay.
And for thrust faults, it was vertical.
Okay, so that's why we get those different fractional orientations.
Exactly.
Okay, got it.
So they use this thing called a Moore diagram
to
analyze this. And it's basically a graphical tool that helps us see when a material is going to fail under different stress conditions.
So it's like a visual representation of how much stress a rock can take.
Yeah, kind of. Yeah. It's more about the combination of stresses, like how much pushing versus how much sliding.
Okay.
It has these lines on it called Moore envelopes, and they kind of define the safe zone.
Okay.
So anything inside the envelopes, the rock is stable.
Okay.
But if you go outside the envelopes, it's going to fail.
It's going to break.
Right.
Okay.
And they showed that for both normal and thrust faulting, the stress state, it's right on the edge of failure.
Oh.
So it's like it's just barely holding on. And they could use this to predict the angles of the faults, too.
Wow.
Which matched what they saw in the experiment.
Okay. That's amazing.
Yeah, it was really cool.
So we can actually, visually see when a rock's going to fail.
Well, we can use the Moore diagram to analyze the stress state and see if it's close to failing.
Okay, got it.
And we can use it to predict, the angle of the fracture and things like that.
So we can kind of see the future with this?
In a way, yeah. It helps us understand how rocks behave under stress.
Got it.
So another thing that Hubbard and Willis did was they looked at the orientation of hydraulic fractures.
Okay.
And there was a lot of debate at the time about how they formed and which way they would go. But Hubbard and Willis, they argued that hydraulic fractures should propagate perpendicular to the minimum principal stress.
Okay.
Which makes sense if you think about it, right?
Okay.
Because the fracture's going to go in the direction of least resistance. So if you're squeezing something, it's going to break where it's being squeezed the least.
That makes sense.
Right.
Yeah.
And they did these really clever experiments with gelatin to test this.
Okay.
So gelatin, it's like a weak solid.
Okay.
It's easy to fracture.
Okay.
So they used it as an analog for rock.
Okay.
And they injected this plaster of Paris slurry into the gelatin to simulate the fracturing fluid.
Okay.
And then they could see how the fractures formed.
Okay, so they could see the plaster.
Yeah, the plaster would harden
Okay.
and leave these traces of the fractures.
Okay.
So they did 2 different types of experiment.
Okay.
In one, they squeezed the gelatin from the sides, which made the minimum principal stress horizontal.
Okay.
And guess what? The fractures were vertical,
okay,
just like they predicted.
Okay.
And then in the other experiment, they wrapped the gelatin with rubber tubing, which created a vertical minimum principal stress.
Okay.
And what did they see? Horizontal fractures. So it really confirmed their theory.
That's cool.
Yeah, it's pretty elegant.
So what are the main things that they concluded?
Well, they basically said that the orientation of fractures is controlled by the state of stress in the rock.
Okay.
And that in areas with normal faulting, you're going to get vertical fractures. And in areas with thrust faulting, you're going to get horizontal fractures.
Okay.
And that this is all governed by what they called incipient failure, which is basically the point at which the rock is just about to fail. So it's like it's right on the edge of breaking.
So to really understand how rocks behave in these situations, I guess we need to talk about some of the basic concepts, right?
Yeah, absolutely.
Like stress and strain.
Yeah, those are fundamental.
Okay, so what is stress?
So stress, at its most basic level, it's just force per unit area.
Okay.
So if you have a force acting on a surface, the stress is the force divided by the area of the surface.
Okay.
And in geomechanics, we use a convention where compression is positive, which might seem a little weird at first.
Yeah, you'd think pushing down would be negative, but...
Yeah, you would think.
Okay.
But it makes sense because in the Earth, most of the stresses are compressive.
Right, everything's being squeezed.
Exactly. So we can break down stress into 2 components.
Okay.
Normal stress and shear stress.
Okay, what's the difference?
So normal stress is the force acting perpendicular to a surface.
Okay.
Like, if you're pushing straight down on a table, that's normal stress.
Okay.
Shear stress is the force acting parallel to a surface.
Okay.
Like if you're trying to slide a book across a table, that's shear stress.
Okay, so normal is pushing, shear sliding.
Exactly.
Yeah.
And stress is a little more complicated than just a single number.
Okay.
Because it depends on the orientation of the surface you're looking at. So if you imagine a point inside a rock.
Okay.
There are an infinite number of surfaces that pass through that point.
Okay.
And each surface is going to have a different stress acting on it. Okay.
So to fully describe the stress at a point, we need to know the magnitude, the direction, and the orientation of the surface.
Okay.
And that's why we call it a tensor.
Okay, so it's not just one number, it's like a whole set of numbers.
Yeah, it's like a matrix.
Okay.
But in 3 dimensions.
Got it.
So in 2 dimensions.
Okay.
If we know the stresses acting in 2 perpendicular directions, we can calculate the stress on any other plane using some equations that are derived from equilibrium considerations.
Okay.
And then there are these special planes called principal planes, where the shear stress is 0.
Okay.
And the normal stresses acting on those planes are called the principal stresses.
Okay.
And we can find the orientation of those planes and the magnitudes of the principal stresses using some more equations.
Okay.
And this all extends to 3 dimensions too, but it gets a little more complicated.
Okay.
And we can use the more ESCO to visualize this.
Which we'll talk about more in the sidebar.
Okay.
But basically, it's a way to plot the stress state on a graph.
Got it.
And see how close it is to failing.
Okay.
And there are also these things called stress invariants, which are quantities that don't change, no matter how you rotate the coordinate system.
Okay.
And 2 important ones are the mean stress, which is the average of the 3 principal stresses, and the octahedral shear stress, which is related to the distortion energy in the rock.
Okay.
And these are used in failure criteria.
Got it.
So that's stress.
Okay, so now we know about stress, which is the force. What about strain?
So strain is the deformation that results from stress.
Okay.
So when you apply a stress to a rock, it's going to change shape.
Right.
And that change in shape is the strain.
Okay.
And we can break down strain into 2 components.
Okay.
Longitudinal strain and shear strain.
Okay, and what are those?
So longitudinal strain is the change in length of a line segment relative to its original length.
Okay.
So if you pull on a rubber band, it gets longer.
Right.
That's longitudinal strain.
Okay.
Shear strain is the change in angle between 2 lines that were originally perpendicular.
Okay, so if you imagine a square and you push on one side, it becomes like a parallelogram.
Right.
And the angles change.
Exactly. That's shear strain.
Okay.
And strain is dimensionless.
Yep.
It's a ratio of lengths or angles.
Okay.
And we use a convention where positive strain means compression.
Okay, just like with stress.
Right.
Okay.
And we can also define principal strains, which are the longitudinal strains acting on planes where the shear strain is zero, just like with principal stresses.
Okay, so there's kind of this parallel between...
Yeah, there's an analogy, but it's not perfect.
Okay.
Because with stress, we have to satisfy equilibrium equations, which basically means that the forces have to balance. But with strain, we have to satisfy compatibility equations, which means that the deformed body has to stay continuous. It can't have any gaps or overlaps. And that puts some constraints on how strain can vary within a material.
Okay, so those are some of the basics of stress and strain.
Right.
Now, you mentioned the Mohr circle before. Can you dig into that a little bit more?
Yeah, so the Mohr circle is basically a graphical way to represent the stress state at a point. And it's really useful for seeing how close a rock is to failing. So we can plot the normal and shear stresses on a graph. And the points on the graph represent the stresses acting on different planes. And then we can draw a circle that passes through all those points. And that's the Mohr circle. And the center of the circle is the average of the two principal stresses. And the diameter of the circle is the difference between the two principal stresses.
So the bigger the circle, the more stress.
Well, the bigger the difference between the principal stresses, which means there's more shear stress, which is what usually causes rocks to fail.
Got it.
And the points where the circle intersects the horizontal axis are the principal stresses, and the highest and lowest points on the circle are the maximum shear stresses. So it's a really handy way to see the whole stress state at a glance.
Got it.
And we can use it to predict, like, the angle of the fracture and things like that.
So this Mohr circle is a powerful tool.
It is. It's a fundamental tool in rock mechanics. And it helps us understand how rocks behave under stress.
So now we know how to visualize stress. So I guess the next question is, like, how do rocks actually respond to stress?
Right. So that's where we get into the relationship between stress and strain. Which is described by constitutive equations. And there are a lot of different theories about how rocks behave. But the simplest one is linear elasticity.
So that's assuming that the rock is perfectly elastic.
Right.
Like a rubber band.
Yeah, exactly. So if you apply a stress and then remove it, the rock goes back to its original shape. And the relationship between stress and strain is linear.
So if you double the stress, you double the strain.
Right. And this is often used in hydraulic fracturing models because it's relatively simple.
Because you're not going to want to model all this complex stuff.
Right.
So, but real rocks aren't always perfectly elastic, right?
No, they're not. They can behave in more complicated ways, especially at high stresses. So there are other theories, like plasticity, which accounts for permanent deformation, and damage mechanics, which accounts for the formation of micro cracks, and creep, which accounts for time-dependent deformation. But we'll stick with linear elasticity for now, because it's a good starting point. So if you imagine a cylindrical rock sample, and you squeeze it from the top and bottom, it's going to get shorter in that direction, but it's also going to bulge out a little bit on the sides.
Just like if you squeeze Play-Doh or something.
Exactly. So the axial stress is the force divided by the area. And the axial strain is the change in length divided by the original length. And linear elasticity says that these two are proportional. And the proportionality constant is Young's modulus, which is denoted by E. And that bulging out on the sides, that's quantified by Poisson's ratio, which is denoted by nu. And it's the ratio of the lateral strain, which is the change in diameter divided by the original diameter to the axial strain.
So it's how much it bulges out compared to how much it gets shorter.
Exactly. And these relationships can be generalized to 3 dimensions using a set of equations. That relate the stresses and strains. And there's another elastic constant called the shear modulus, which is denoted by G. And it describes the resistance to shear deformation. So how much force it takes to slide one part of the rock past another part. Okay. And there's also the bulk modulus, which is denoted by K. And it describes the resistance to changes in volume. Okay. So how much the rock compresses when you squeeze it from all sides. Okay. And for an isotropic linear elastic material.
Okay, which means that its properties are the same in all direct
right.
tech.
All these moduli are related.
Okay.
So you only need 2 of them to calculate the rest.
Okay.
And sidebar 3C has a table that shows these relationships.
Okay, so it sounds like if we know Young's modulus and Poisson's ratio, we could figure out the rest.
For an isotropic linear elastic material.
Okay.
Yes.
Got it.
But rocks aren't always isotropic.
Right. They can be anisotropic.
Right.
Which means that their properties are different in different directions.
Exactly. And that's often the case in sedimentary rocks because they're formed in layers.
Right.
So they tend to be stronger in the direction perpendicular to the layers than in the direction parallel to the layers.
Okay, that makes sense.
And to describe anisotropic materials, we need more than 2 elastic constants.
Okay.
We need at least 5.
Okay.
And sometimes even more.
Okay, so things get a lot more complicated.
They do.
When you have anisotropy.
Yeah, it's a lot more challenging to model and analyze.
Got it.
So another important thing to consider is pore pressure.
Oh, okay.
Which is the pressure of the fluids in the pores of the rock.
Okay.
And this is important because it affects the effective stress.
Okay.
Which is the stress that's actually carried by the rock matrix.
Okay, so the pore pressure kind of helps to support the rock.
Yeah, it's like it's pushing back
against the overburden stress.
Okay.
So the higher the pore pressure, the lower the effective stress.
Oh, okay. That makes sense.
And this is really important for understanding rock behavior.
Okay.
Because it's the effective stress that controls whether the rock is going to fail or not.
Okay.
So if you have a high pore pressure, it's going to take more stress to make the rock fail.
Okay. Because the pore pressure is helping to hold it together.
Exactly.
Okay.
And this is also important for hydraulic fracturing. Because when you inject fluid into a rock, you're increasing the pore pressure, which can cause the rock to fracture.
Okay, so that's how we create those fractures.
Right.
Okay.
But it can also cause problems.
Okay.
If the pore pressure gets too high, it can cause the wellbore to collapse.
Okay, so you got to be careful.
Yeah, you got to find the right balance between fracturing the rock and keeping the wellbore stable.
Got it.
So there are a couple of different concepts
that are used to describe how pore pressure affects rock behavior.
Okay.
One is drained versus undrained response.
Okay.
So if you apply a stress to a rock very quickly, the pore fluids don't have time to escape.
Okay.
So the rock behaves in an undrained manner, which means that it's stiffer than if it were drained.
Okay.
But if you apply the stress slowly, the pore fluids have time to escape.
Okay.
So the rock behaves in a drained manner, which means that it's softer.
Okay, so it's like if you squeeze a sponge really fast.
Yeah.
It's going to be harder to squeeze than if you squeeze it slowly.
Exactly. And this is important for hydraulic fracturing because you're usually injecting fluid pretty quickly.
Right.
So the rock is going to be in an undrained state.
Okay.
And that's going to affect how the fractures propagate.
Okay, got it.
And then there's the concept of effective stress, which was first introduced by Terzaghi in the 1920s.
Okay.
And he basically said that the effective stress is the total stress minus the pore pressure.
Okay.
So it's the stress that's actually carried by the rock matrix.
Okay.
And this is important for understanding things like consolidation, which is how soils compact under load.
Okay.
But Biot came along in the 1940s and 50s, and he developed a more comprehensive theory, host speaker. Okay, so you're back again for another deep dive, and this time you're here because you wanna get the goods on how we use well logs, like all that geophysical data from drilling, to really get a handle on reservoir stimulation. You want the core knowledge without feeling like you're drowning in like a sea of data, am I right?
That's right.
Think of this deep dive as like your express lane to understanding a crucial piece of how we get energy out of the ground.
Yeah, I think our mission today is super clear. We're gonna pull out the key takeaways from the ch4.pdf, showing precisely how those well logs get used to build up this like detailed picture of what's going on down there before we even touch it with any kind of stim treatment, right?
Yeah.
It's like scouting out the playing field before we make our big move.
Now, I think it's really important to be clear on what we're not covering today. Well, logs are super valuable for figuring out like how much oil and gas are actually down there in the first place. But that's a whole nother beast, a whole nother deep dive. I mean, what makes our topic today kind of special is that we don't just fixate on those like juicy hydrocarbon-bearing zones, the pay zones. For stimulation, we've got to understand the rock layers right next door, what we call those bounding layers, because they actually play a huge role in how our treatments behave.
Absolutely. I mean, yeah, our ultimate goal here, right, is to build this thing called a formation model. Imagine a stack of pancakes, right? Each pancake represents a layer of rock, and each of those layers has its own set of properties. Now, these properties might be consistent throughout the whole pancake, or we might, have to use some kind of average value, or even have them change, like predictably with depth, like how the pressure of the fluids might increase as you go deeper down. Figure 4.1 in our source actually shows this layered pancake idea really nicely.
Okay, so let's unpack these properties a bit. I mean, these properties, they kind of fall into two main camps, right? First, we've got those that tell us about how easily fluids can actually move through the rock. It's like how porous and permeable as sponges, right?
Yeah, exactly.
And then second, we've got those properties that describe how the formation is going to react when we start like messing with it, pushing and pulling, like how stiff or brittle it is. We're gonna get into the nitty-gritty on both of these.
And the very first step, right, the very first step in piecing together this whole layered picture is to use the data from those well logs to estimate those crucial properties within each pancake, each layer.
Okay. All right. So we know what we're after and why it matters. Let's get down to brass tacks here. First thing that might sound simple, but actually has some wrinkles per me. Depth. When we're talking about like how deep something is in an oil field, there are actually a couple of ways we measure it, and it really does impact how we build that formation model.
And this is where it gets really cool, because you have this difference between true vertical depth, or TVD, and measured depth. We call that MD. Yeah. TVD, you could think of it as that straight line distance down, like dropping a plumb bob, a weight on a string.
Yeah.
It's a unique measurement and super, super important because, when we're figuring out how high a fracture might go or exactly where to put those treatment fluids, TVD is our guide.
Right. It's the absolute vertical position. Okay. Now, measured depth, that's the total distance along the path the drill bit took to get down there. Since most wells aren't perfectly straight, that MD is usually longer than TVD. And it's not unique either because it depends on how we're measuring it, like the length of the drill pipe that's been put in.
Yeah.
Now, MD, that's super important for things like calculating, like how much friction our fluids encounter as they go down, or how much we got to pump to displace what's already down there.
And then to make things even more interesting, we have logging while drilling data. We call that LWD. This is information about the formation. It's recorded as we drill, real time. But the catch is this data initially it's recorded against time, not depth. So we got to be careful, very careful when we line it up with measurements taken at specific depths later on.
So the big takeaway here is we need to make darn sure that all of our log measurements are referenced to a single consistent measured depth. We usually pick a log like the gamma ray log that gives us a natural radiation reading or an imaging tool log to be our common reference point.
And then to connect MD to that all-important TVD, we use the well's deviation angle. It's simply how much the well bore is tilted away from vertical. In equation 4.1 in our source, it actually shows how a tiny change in TV is equal to that tiny change along the well bore, MD, multiplied by the cosine of that angle. So we can, add up all those little changes along the well's path to get the total TVD from the MD.
Okay, now let's add another idea here. Formation dip. Those pancake layers we talked about, well, imagine they're not perfectly flat, right? They're tilted at an angle. We call that angle delta. And this gets really interesting when we have deviated wells, those that aren't straight down, and when the rock layers themselves are tilted.
Yeah, so how do we actually compare information from different wells if they're drilled at different angles and the rock itself is tilted? And that's where this idea of true bed thickness comes in. We call that TBT. Think of TBT as the real perpendicular thickness of that rock layer, no matter how the well of the war cuts through it.
Yeah.
It gives us a standard way to compare the thickness from different wells.
Exactly. And equation 4.2 shows how TBQ relates to MD. So a tiny change in TBT is the change in MD times the cosine of both the well deviation angle and that formation dip angle, delta.
So to summarize, right, when we're talking about the inherent properties of a layer, like how much fluid it can hold, porosity, or how easily fluids flow through it, permeability. Those are related to that true bed thickness. But when we're thinking about the vertical extent of a fracture, or like exactly where to place our treatment, we're thinking about true vertical depth. And it's really important to remember that if the rock layers are perfectly horizontal, then TVD and TBT are the same thing.
Right.
And Figure 4.2 actually does a great job of visualizing how the angle of the well and the tilt of the rock layers can really change how these logs look when we plot them.
Okay. So we've kind of gone through depth and all its different flavors. Now let's talk about heat, specifically formation temperature. Why is knowing the temperature down there so important for reservoir stim?
It's fascinating how temperature directly impacts how the fluids and the chemicals we use behave. Both for matrix stim, where we're trying to improve flow in existing pores, and frashing, where we're making new pathways for those fluids to flow. And these fluids, right, they can react differently at different temperatures. So knowing the downhole temperature is absolutely critical for designing a treatment that'll actually work as planned.
So how do we actually measure the temperature way down there in the earth? Our source mentions that the temperature of the drilling mud when we run wireline logs is often used as like a starting point.
Yeah, that's true. But you got to keep in mind that the mud temperature is usually a lower estimate. It can be a lot cooler than the real formation temperature, sometimes by as much as 30 degrees Fahrenheit, which is about 15 degrees Celsius. But the problem is it's often the only continuous temperature reading we get along the whole well bore.
Luckily, we have other ways to get a better idea, right?
Exactly. So when we use formation testers to grab fluid samples from specific zones, right, those tools are also constantly watching the temperature of the fluid that's coming in.
Right.
And that gives us one of the most accurate readings we can get, but it's only at those specific points, right?
Yeah.
And another good estimate comes from the bottom hole temperature that's recorded by a special gauge that we run on a slick line, which is basically a thin wire line after we've perforated the well, right? And we're starting to get some flow from the formation.
So it sounds like we're piecing together this temperature profile down there using a combo of these different methods. All right, now let's move on to that first category of formation properties. Those related to how fluids move through the rock, what we call fluid diffusion. So what are the big ones, the key properties we got to focus on?
Well, our forest tells us, right, the main ones are porosity, permeability, pore pressure, and then the actual types of fluids that are present. And it's worth noting that while those logs give us tons of information, we can't directly measure things like how thick or thin the fluids are. That's viscosity. Or how much they change volume under pressure, compressibility, just using those standard logs.
Okay. Let's start with porosity, since it's a word that gets thrown around a lot in the oil and gas world. So what is it, simply put?
You can think of porosity, we often use the Greek letter psi for it, as the empty space within the rock. So it's the fraction of the total rock volume that's filled with fluids, whether it's oil, gas, water, or a mix, right?
Right.
And porosity can range from almost zero, like in a really solid rock like salt, to 40% or even more in looser formations like some shales or sandstones. And it's really a fundamental property because it tells us how much fluid a given volume of rock can hold.
So how do we measure this super important property using logs?
Now, the thing is, no single log directly measures porosity. Instead, we use a bunch of geophysical methods, both wireline tools that we run after drilling, and then LWD tools that collect data during drilling to measure other properties that are related to porosity. And then we use established relationships to estimate it. And the details of processing that data, that can get pretty hairy. And it's beyond what we're going to talk about today. But our source, it does mention a great reference for that if you're interested. Kurin et al., 1986.
Our source also mentions primary and secondary porosity. What's the difference between those two, and why does it matter?
Okay, so primary porosity, that's the original pore space that was created, when the rock was first formed. Like the gaps between grains of sand, or even within the particles themselves. Yeah. Now, secondary porosity, on the other hand, that develops later. And it's due to, geological processes like fracturing or the dissolving of parts of the rock. And when we're trying to connect porosity to other rock properties, like its strength or how easily fluids flow, we're usually more interested in that primary porosity. Because those relationships often depend on the initial rock structure.
Makes sense. And then there's also total and effective porosity. What's the difference there?
All right, so total porosity, that's exactly what it sounds like. It's all the fluid-filled space in the rock. But not all that fluid can necessarily move, right?
Yeah.
Some of the water...
Okay, so no single log just spits out a porosity reading, but we get there through other measurements, right? So let's talk about some of those methods. The first one our source mentions is density logs. How do those help us?
Well, so density tools, they basically measure how dense the formation is. It does this by measuring how easily electrons in the formation scatter gamma rays.
Okay.
It's a pretty shallow measurement, just looking about half a foot into the formation. And it's usually sensing what we call the flushed zone, where the original fluids have been pushed away by, drilling mud filtrate.
Yeah.
If we know the density of the solid rock and the density of the fluid in the pores, which we often just approximate as the density of the mud filtrate, we can use this volume balance equation 4.3, to calculate the total porosity.
Right.
But here's the catch. If there's gas, which is much less dense than oil or water, density logs tend to overestimate the pore space.
Okay. Next up is porosity from neutron logs. What are those telling us?
All right, so neutron logs measure the concentration of hydrogen atoms in the formation. And these are also shallow, looking about a foot into the formation. And the idea is most of the hydrogen is going to be in those formation fluids, the water and hydrocarbons.
Yeah.
And the rock matrix usually has very little hydrogen. So if we know the hydrogen content of the fluid, the neutron log can give us an estimate of total porosity. Interestingly, water and liquid hydrocarbons, they have pretty similar hydrogen indices, so neutron logs aren't very sensitive to the presence of oil. But just like density logs with gas, neutron logs underestimate porosity if there's gas.
So it sounds like density and neutron logs, they kind of have like opposite reactions to the presence of gas.
That's exactly right. And that's why often a simple average of the porosity values we get from density neutron logs, as shown in equation 4.4, can be a pretty good first guess for that effective porosity, especially in simpler underground environments.
Okay. What about sonic logs? How do they fit in?
So sonic logs measure how fast sound waves travel through the formation. Basically, the time it takes for a sound wave to travel a certain distance, which we call transit time, and the presence of fluid in the pore spaces, it actually slows down those waves. So if we know the speed of sound in the solid rock and in the fluid, we can use equation 4.5 to estimate the total porosity. Now, sonic logs, they also have a relatively shallow depth of investigation, about a foot. So we usually assume the fluid is that mud filtrate. However, sonic porosity estimates can be sensitive to what kind of fluid is in those pores. So if there's hydrocarbons, the estimate might be off. On the plus side, sonic porosity is mainly sensitive to the primary porosity, not the secondary porosity that developed later.
Okay, so our source also mentions this NMR, nuclear magnetic resonance, for estimating porosity.
Yeah. So NMR, those tools measure how quickly the nuclei of hydrogen atoms in the formation fluids, how they relax back to their original state after being, briefly aligned by a magnetic field. And the porosity we get from NMR, it's related to that amount of hydrogen, similar to neutron logs. But it's mainly influenced by those fluids that are actually movable. So estimating porosity from NMR data, it involves some pretty fancy analysis. But it's got two big advantages. First, because it's focusing on the movable fluids, it gives us a good estimate of that effective porosity. And second, it's really good at giving us reliable porosity estimates in formations that have a lot of shale, which can be tricky for other locking methods.
Okay, we've covered density, neutron, sonic, NMR. The last one mentioned for porosity is resistivity. How does that work?
So the idea here is that if we assume the rock itself doesn't conduct electricity, then any conductivity we measure is mainly due to that salty water, that brine in the pores. And we use this idea called the formation factor, F, which is, it's the ratio of the resistivity of the rock when it's totally full of brine to the resistivity of that brine itself, as shown in equation 4.6. Now, back in 1942, Archie, he developed this empirical relationship, equation 4.7, that links that formation factor to the total porosity using two constants, A and M, and those depend on the type of rock. So by combining those two equations, we can solve for porosity, as in equation 4.8. But our source does warn us against relying too much on this method for porosity alone, because it's super sensitive to the type of fluid in the formation, especially, the amount of hydrocarbons, which are very resistive, and also to the presence of any conductive minerals in the rock.
So it sounds like to really get a grasp on porosity, we can't just hang our hat on one single log.
Yeah.
We've got to look at a bunch of them, right?
Absolutely. We get the best results when we do what we call synergistic processing, where we look at how each tool responds to the formation, and we really try to tailor our analysis to the specific geology. Now, if we don't have, the luxury of that kind of processing, then like we mentioned earlier, a simple average of density and neutron porosity can be a decent starting point, especially in less complicated situations. And NMR porosity is often a better bet in more challenging formations.
All right, so we've really gone in depth, no pun intended, on porosity. Now let's talk about lithology and saturation. Our source says these are key pieces of the puzzle for designing matrix acidizing treatments and also for building our models of the stress in the formation. And for freshing, knowing the fluid saturation, that helps us estimate how compressible the fluids are. So let's start with saturation. What is it and why do we care?
So saturation, specifically water saturation, which we usually call settled W, it's simply how much of the total pore space is taken up by water. Okay. So by definition, 1 minus W gives us the fraction that contains hydrocarbons, the oil and gas. We're also really interested in what we call irreducible water saturation, SWIN, which is that water that's basically stuck to the rock can't be moved. Both porosity and saturation, they're really fundamental in evaluating a reservoir because when we multiply them together, we get an idea of the actual volume of hydrocarbons in place. And for stimulation, these properties also indirectly control how water-based fluids are going to flow through a rock that already contains some water and hydrocarbons, right? And the relative ease with which water can flow compared to hydrocarbons, we'll talk about that soon, that's also linked to saturation. And as you mentioned, saturation helps us estimate how compressible the fluids are. We need to know that to understand how fluids might leak off into the formation during a frac job.
So how do we go about determining that water saturation's W?
Well, the main way we estimate it is through resistivity measurements. Now, in a clean formation, meaning one that doesn't have a lot of shale or other conductive minerals, the ability of that formation to conduct electricity is mainly due to, that salty water, that brine that's in the pore spaces. Remember, conductivity is just the opposite of resistivity. And Archie, he came up with this experimental relationship equation 4-9 that connects the true resistivity of the formation, RT, which is the resistivity far away from the wellbore, to the water saturation. And this equation has a bunch of constants, A, M, and N. And those depend on the specific rock we're talking about.
Now, our source mentions that resistivity is often measured at different depths of investigation around the wellbore. How does that help us with saturation?
Well, because we have resistivity tools that can basically see different distances into the formation, right? We can get a reading in the zone right around the wellbore that's been flushed by mud filtrate, ARCSO. But we can also get a reading deeper in the virgin formation, the part that's not been affected by the drilling, that's RT. And that lets us use equation 410, which relates those two measurements along with the resistivity of the mud filtrate, RMF, to estimate water saturation. Now notice that this equation doesn't actually involve porosity directly, which can be handy. We typically use a value of 58 for alpha in that equation. And we can get the resistivity of the formation water itself, RW, from things like water analysis reports, samples of the produced water, or even from other logs like SP logs.
What happens if we're not dealing with these clean formations? What about rocks that have, conductive minerals like clay in them?
That's a great point. Those conductive minerals can really throw off our simple resistivity-based saturation estimates because they provide another path for electricity to flow, making the formation look more conductive than it really is due to the brine in the pores. So there are techniques, we call them weighted average techniques, that try to correct for those minerals, especially in shaly formations. And our source mentions Poupon et al. 1970 as a good reference for those. But in really complex situations, the best way to get a handle on water saturation is often through a detailed analysis of the types and amounts of minerals that are actually there in the rock, what we call, lithological analysis, which is what we'll talk about next.
Okay, so let's dig into lithology. What's the main objective when we do a lithological analysis using logs?
All right, so the main goal is to figure out, the volume percentages of all those different minerals and fluids that make up the formation and how they change with depth. And our source kind of introduces this with a classic example, right? A sequence of sand and shale layers. Historically, a lot of focus has been on those types of formations. And one of the simplest things we try to determine is a shaliness indicator, basically how much clay is present compared to clean sand.
And how do we get that shaliness from logs?
Well, the most basic way is to look at the gamma ray log. And the idea is those clay minerals often contain naturally radioactive elements. So high gamma ray readings above a certain threshold tend to indicate the presence of shale, while low readings suggest cleaner sandstone. And values in between, they usually represent, mixtures of sand and clay. Now, we can try to make this more quantitative by using a simple response equation for the gamma ray tool, as shown in equation 411. This equation relates the gamma ray reading in GRPI units to the percentage of potassium oxide, K2O, which is often found in clay minerals. So for a really simplified mineralogical model, one that maybe just considers quartz and a potassium-bearing clay, we can use this to estimate those relative amounts.
So it sounds like different logging tools, they respond to different things in the rock and fluids.
Exactly. Tools that work on different physical principles will respond to different combinations of atoms, minerals, right?
Okay.
And for each type of tool, we can come up with a mathematical relationship or response equation. And that equation might be, more complex than our gamma ray example, but it'll always involve the volume fractions of those minerals and fluids we think are down there, as shown in equation 412. And each log we run gives us one of those equations. So if we run a bunch of different logs, we end up with a system of equations, often nonlinear, that we can try to solve to get the volume percentages of those different components. And our source actually mentions Courin et al., 1986, again, as a reference for how to do this.
But I imagine it's not just as simple as solving equations, right? We got to have a sense of what minerals might be there in the first place.
You got it. We have to make some educated guesses or assumptions about the mineralogy of the formation before we even begin. First of all, mathematically, we can't solve for more minerals than we have equations.
Right.
So fewer logs mean a more limited number of minerals we can reliably identify. Second, and this is really important, there's often no single unique combo of minerals that perfectly explains all the readings we get. Several different mixtures might give us responses that look really close to our measurements. But those different models could lead to very different predictions about, permeability or strength. So that's why it's super important to come up with a plausible model before we start. And that model needs to be checked by a geologist, someone who knows the area, to make sure it makes geological sense. Figure 4.3 actually shows an example of what that output might look like, a breakdown of the volume percentages at different depths. But our source also warns us that even though that volumetric information is really useful for building like pressure or stress models, we got to be careful when we try to use it to figure out things like mechanical properties or understand which zones are actually connected. Just knowing the volume of sand and shale, for example, doesn't automatically tell us how strong that rock is, or whether fluids can flow easily between those layers.
All right, we've covered porosity, lithology, saturation, all key for understanding how fluids are hanging out and moving in the formation. Now let's move on to permeability, which is, all about how easily those fluids can actually flow through the rock. What's the basic definition here?
Permeability it's exactly that. It's a measure of the rock's ability to transmit fluids. The standard unit is square meters, but in the oil field, we almost always talk about millidarcies, MD. Think of it like a measure of how much resistance the rock offers to flow.
Okay, now our source mentioned that permeability is a tensor. What does that mean, practically speaking?
So that essentially means that permeability isn't always the same in all directions. It depends on which way the fluid's trying to flow. However, if we don't have a ton of natural fractures or the stresses aren't crazy different in different directions, we often assume that the permeability parallel to the bedding, which in our simple model we're assuming is horizontal, that it's isotropic, meaning it's the same in all horizontal directions. But if we do have a lot of fractures or big differences in stresses, then permeability can vary, and fluid might flow easier in one direction than another. Now, the permeability perpendicular to the bedding, what we call vertical permeability, or KV, that's often a lot lower than the horizontal permeability, KHE, especially in the sandstone reservoirs. In rocks with really fine layers, laminated sandstones, the vertical permeability can be like orders of magnitude smaller. But in some carbonates, KV can actually be equal to or even greater than KH. So unless we need to get specific about direction, when we just say permeability, we usually mean the horizontal permeability, KH. But for certain things, like analyzing flow in horizontal wells or multi-branched wells, we might need to consider both KH and KV, and even the different horizontal components of KH. For your standard vertical well, KH is usually enough.
Okay, what about when we have more than one fluid, like oil and water together? How does permeability play out then?
Right, so that's where this idea of relative permeability comes in. If we say K is the absolute, its ability to conduct a single fluid when that fluid completely fills the space, Then the relative permeability to water, CAC, is the ratio of how easily water flows when oil is also present, CAC, to that total permeability, as shown in equation 413.
Yeah.
And similarly, the relative permeability to oil, CRO, is the ratio of how easily oil flows when water is also present, CO, to that total permeability, as shown in equation 414. Now, these relative permeabilities, they're not constant. They usually depend on how much water is in the formation. That water saturation stub you figure 4.4 actually shows a typical relationship. For example, the Park-Jones relations given in equations 415 and 416, they provide ways to estimate CRO and CRO as a function of ton W, where M is a common value, and then A and B are parameters that we usually got to determine by calibrating with lab measurements on core samples. And to get the actual permeability to water or oil under those conditions, we just multiply that total permeability, K, by the respective relative permeability. We also need to know that irreducible water saturation, SWI, which is the minimum amount of water that's always going to be trapped in the pores. And we can get that SWI from lab measurements on cores, or sometimes using NMR logs in hydrocarbon zones. We usually assume it's 1, meaning 100% water, no hydrocarbons in zones that don't have hydrocarbons.
Okay, so in the context of reservoir stim, what are the most important things about permeability we need to know?
Since a lot of stim treatments involve injecting one fluid to push out another, we're really interested in what we call endpoint permeabilities. That's the permeability to oil when we've got like the max amount of oil present, and the permeability to water when we've got like the max water saturation. And these endpoint permeabilities, they can be very different. When we're deciding if a well's a good candidate and when we're checking how well the treatment worked, we're mainly looking at the permeability to the hydrocarbons that are already there. But when we're actually designing and doing the treatment, we're more interested in the permeability to the fluids we're injecting, which, are often water-based.
Okay, so how do we actually measure permeability? Our source talks about indirect and direct measurements. What's the difference there?
So direct measurements of permeability, we get those mainly from formation testing, and those give us actual values at specific spots in the well. Indirect measurements, those give us a continuous log, but they always need to be calibrated, either using those direct measurements or lab measurements on cores.
Okay, let's start with the indirect ways we estimate permeability from logs. What are some of the key methods?
So our source highlights a few techniques, and they all kind of rely on some form of calibration, often by comparing log-derived estimates to permeability values measured on core samples from a water-saturated zone. These are really valuable for filling in the gaps between those direct measurements and giving us a continuous picture. One common approach is to use these empirical correlations that relate permeability to porosity and sometimes also to water saturation. Equation 417 shows a general form of these relationships where Cx and Y are constants, and they depend heavily on the rock type and the size of the grains. It's really important to understand that these correlations, they got to be developed and calibrated for the specific geology we're working with. But once we have a reliable one, it can give us pretty good continuous estimates of permeability within the same field. And sidebar 4A actually shows a good example of why we need to be so careful about using like generic correlations without calibrating them locally.
Another indirect method, this one connects permeability to both lithology and porosity through what's called a characteristic length scale, lambda, denoted by the Greek letter S. This length scale is related to the average size of those pore throats, those narrow passages that the fluids have to squeeze through. For formations with higher permeability, generally above 100 millidarcies, the Calenda model shown in equation 418 provides a decent estimate with the constants C and M, again, depending on the formation. And for rocks with lower permeability, we often have to apply some corrections.
Welcome to the deep dive. We're diving deep into hydraulic fracturing, a topic that's, well, pretty much unavoidable these days. But what exactly is it, and why is it so crucial for, actually getting those resources out of the ground?
Right.
Today, we're going to try to really unpack this whole hydraulic fracturing thing as a key engineering tool, and luckily, you've sent us a ton of great sources to help us get into it.
Yeah, hydraulic fracturing is a primary, method that engineers use to improve, productivity. And there are three main ways that it achieves that. The first is that it creates like a conductive channel. Imagine like clearing out debris in a tunnel. Except in this case, it's clearing a path past any damage that's right near the wellbore.
Okay, makes sense. So that's the first thing. The second thing you mentioned is that this channel is not just, a quick fix at the entrance. It extends deep into the reservoir itself.
Right. It reaches resources that, we wouldn't be able to produce otherwise.
So you're basically making, like, a much longer, well, almost, but horizontally.
Yeah, in a way.
Okay. And the third thing then is that fracturing can also be used for reservoir management, right?
Exactly. That includes things like consolidating loose sand, like you don't want that flowing into the wellbore and clogging things up. And it also means like implementing strategies to increase the total amount of hydrocarbons we can recover,
Sure.
Over the life of a field.
So, it sounds pretty straightforward at first glance. You pump in some fluid, you crack the rock, more oil and gas comes out. But as these sources point out, geology is never that simple.
Right.
It seems like this is a super multidisciplinary kind of process.
Absolutely. You've got your production engineers who understand how to get the fluids out. You've got your rock mechanics people who can, figure out how the earth is going to fracture under all this pressure.
Yeah.
Then there's the fluid mechanics folks who know how liquids behave under, very high pressures, especially way downhole. And then on top of that, you have to have people who are good at choosing the right fluids and solids and the material science folks. And then obviously the operations teams who have to execute all of this out in the field.
Yeah, it's a lot of people.
Yeah. It's a huge collaboration.
It's a big team.
And one of the things you hear a lot in this field is there's no rule of thumb. Every fracturing job needs to be tailored to that specific well and reservoir.
Okay, well, let's actually get into what's happening down there. What actually happens in a fracturing treatment? Our sources explain it as basically injecting fluid into the well so fast that it can't leak off into the surrounding rock fast enough. So then what happens?
Well, because that fluid's trapped, the pressure builds up inside the wellbore.
Right.
And eventually that pressure gets high enough to overcome the strength of the rock. Obviously the steel casing of the well is much stronger than the rock, so the rock's going to break first.
Right.
And that's when you create your fracture. And in most vertical wells, you end up with a vertical fracture, like a planar fracture. And that's because the minimum horizontal stress, which is like the smallest force pushing on the rock, is typically horizontal. So the fracture opens perpendicular to that.
Okay. So now we've got this crack in the rock. How does it actually grow? And more importantly, how do you keep it open after you stop pumping all that fluid in?
Well, once that initial crack forms, right, it exposes a lot more surface area to the pressurized fluid.
Okay.
So more fluid wants to leak off into the rock. But as long as we keep pumping fluid in faster than it's leaking off, the fracture's forced to grow further and further into the reservoir.
Right, so it's got to be a really high pumping rate.
Yeah.
Okay, but even if you make this long crack, as soon as you stop pumping, the pressure drops. And wouldn't the fracture just close back up?
Exactly, and that's where the proppant comes in.
Okay.
Usually it's sand. Sometimes they use engineered particles, but usually sand. And it's mixed in with the fracturing fluid. So as we're pumping, the proppant gets carried deep into the fracture. And then when we stop pumping and the fluid flows back out of the well, the proppant is left behind. It's trapped in the fracture, and that keeps it propped open.
Okay.
So now you have this permanent pathway, this high conductivity pathway for the oil and gas to flow back to the wellbore. There's also something called acid fracturing that they sometimes use in carbonate rocks. In that case, instead of using proppant, the fluid itself is acidic. So it actually dissolves, channels in the rock.
So that's a different mechanism.
Yeah.
Our sources talk a lot about this idea of fluid loss. Why is that such a big deal in fracturing?
Well, you see, while we're creating and growing this fracture, a lot of the fluid we pump in leaks off into the surrounding rock. And that can really, hinder the growth of the fracture, especially early on when it's still relatively short and close to the wellbore.
Right.
So to combat that, the first fluid we pump downhole is actually just the base fluid without any proppant. And this is called the pad.
Oh, so the pad is prepping the fracture, kind of?
Yeah, you can think of it that way. The main job is to get the fracture initiated, get it propagating away from the wellbore, and then establish enough penetration and width so that when we start pumping the proppant, it can actually travel further into the formation without getting stuck or losing too much fluid right at the tip of the fracture.
So it's making sure there's actually space for all that proppant to go.
Exactly.
Okay, and then after the pad, you start actually introducing the proppant.
Right.
How does that work? How do you manage that?
Yeah. Well, we don't add it all at once. We start with a low concentration of proppant in the fluid, and as we pump that into the fracture, it starts to flow towards the tip. And because there's a lot of fluid loss happening at the tip, that proppant-laden fluid can actually, catch up to the tip.
Oh, interesting.
And as those proppant stages move down the fracture, they're constantly losing fluid to the formation. So the concentration of proppant inside the slurry actually increases as it travels.
Okay.
And of course, the concentration of proppant we're pumping from the surface is increasing too as we go through the stages. The idea is to time it so that the very first stage of proppant reaches the fracture tip right when the last of that pad fluid leaks off. And by then, the concentration of that proppant stage has increased to the target concentration we want.
So it's a pretty delicate process.
Yeah, it is. The goal is that by the end of pumping, the entire fracture is filled with the designed concentration of proppant.
I see, so it's all planned out.
It's a carefully choreographed dance.
Our sources also mentioned something called tip screen-out fracturing. How is that different from what you just described?
So what I just described is what we would call normal fracturing design.
Yeah.
In a tip screen-out, or TSO, we actually keep pumping, even after the fracture has pretty much stopped growing in length.
Mm.
We keep pumping that proppant-laden fluid in, and since the fracture can't get much longer, it's forced to get wider. Like, imagine trying to stuff more and more into a bag that's already full. It has to stretch.
Right. So you're basically packing it in.
Yeah. And in certain situations, that extra width can be really beneficial for production.
Okay, so at the end of all this, after all this intricate engineering, what does a successful hydraulic fracture actually look like? What are we aiming for?
The ideal outcome is a fracture that's filled with proppant, has a certain productive length, we call that XF, a certain propped height, and, most importantly, a certain propped width.
Right.
And that propped width is what determines the fracture's conductivity or how easily fluids can flow through it, which we denote as KOW. And just to be clear, that productive half-length might actually be shorter than the total length of the fracture that we created.
Okay, so we've talked about what hydraulic fracturing is. We've talked about how it's actually done. But now let's talk about the why. Why go through all this trouble and expense?
Right.
What are the main goals here? Our sources highlight 3 big reasons.
Right. So the first is damage bypass. We touched on that earlier.
Right.
Remember, damage from the drilling process or just naturally occurring stuff can really hurt a well's ability to produce. So by creating this highly conductive fracture that cuts through that damage zone, we're essentially, giving those reservoir fluids a nice clear path to flow into the well.
So you're removing a bottleneck.
Yeah, exactly.
Now, our sources also talk about something called matrix treatments. They mention those as another option for dealing with near wellbore damage. So when would you choose fracturing over something like a matrix treatment?
Well, matrix treatments, those involve injecting fluids that either dissolve the damaging materials or just remove them, and that's often the first thing you try. But they don't always work. Like if the damage is really extensive, or if it involves some sort of physical blockage that the fluids can't get through, or even if the damage is just not soluble, then you have to do something else. And that's when hydraulic fracturing can be a much better solution. You're basically creating a whole new flow path, right?
Makes sense. So the second reason for fracturing is not just to fix damage, but to actually improve the well's productivity beyond what it would normally be. How does it do that?
Well, unlike matrix treatments, which are just trying to restore the original permeability, right? Hydraulic fracturing creates this long channel that extends deep into the reservoir. So now you have a much larger surface area of the formation that's connected to wellbore.
Okay.
And to understand how that leads to more production, you have to look at Darcy's law. Right. It's a basic principle that describes how fluids move through porous media, like, reservoir rock. And it says that the rate of flow is proportional to the permeability of the rock, the area available for flow, and the pressure difference driving that flow. And then it's inversely proportional to the distance the fluid has to travel. So by fracturing, we're increasing that flow area significantly. And it's not just about making it bigger, it's also changing the shape of the flow, making it much more efficient.
Okay.
So it's all about economics, right? You want to get the most oil or gas out for the cost of the treatment.
Right. You want a good return.
Exactly.
And then the third major application is reservoir management. This seems to be more about managing the whole reservoir, not just a single well, right?
Exactly. Fractures can be a powerful tool for controlling how fluids move within the entire reservoir. It can really change decisions about where to drill new wells, how many wells you need to drain a reservoir, and how to get the most hydrocarbons out of the whole field. This is especially important in tight low permeability formations where the oil and gas just doesn't flow easily on its own.
Our sources give a really interesting example of this reservoir management idea with the Gulf-X field and something called an indirect vertical fracture completion, or IVFC. Can you walk us through that?
Yeah, so the Gulf-X field had some unique challenges. It had this highly permeable upper zone and then a lower zone with moderate permeability. Early production focused on the upper zone, but that led to problems like sand production. Basically, you have loose sand flowing into the wellbore, which you really don't want.
Right.
And they also had early water breakthrough, where water from an aquifer started flooding the producing zones way too soon.
Oh, so that's bad.
Yeah, it really limited how much oil they could ultimately recover from the lower zones, which actually had significant reserves. They could use gravel packing to address the sand issue, but that wasn't ideal for the lower zones, which needed stimulation to be economic. And the water breakthrough also caused scaling, which would plug up those gravel packs anyway. So it was a tricky situation.
It sounds like it.
Yeah.
So how did this IVFC technique solve those problems?
Well, instead of directly producing from that troublesome upper zone, they initiated a hydraulic fracture from a deeper, more stable zone.
Okay.
And this fracture grew vertically, connecting both the upper and lower zones.
Interesting.
This approach was pretty clever. First, it allowed them to still get some production from the main upper zone to meet their short-term targets.
Okay.
But it also stimulated the lower zone, helping them recover more oil from there. And because that weak upper zone was no longer being directly produced from, the sand production problem was significantly reduced.
I see.
Plus, the fracture acted as a barrier to water, delaying breakthrough. So they were able to produce more oil for longer.
It sounds like a win-win.
Yeah, it was a very successful application of hydraulic fracturing.
And what's really fascinating, our sources say that in this case, they had to be careful about how conductive they made the fracture. Like, they didn't just want the most conductive fracture possible.
Right. If the fracture was too conductive, it would have actually produced too much from the upper zone, and that would have just made the water breakthrough problem worse. Plus, there were limits to how much they could actually produce from the well anyway because of, surface facilities and the size of the production tubing.
Okay.
So a super high conductivity fracture wouldn't have necessarily meant more oil in the long run. They really had to fine-tune that conductivity to balance the reservoir and the well's limitations.
That's fascinating. I mean, it really shows how complex this all is.
Yeah.
It's not just about making the biggest crack you can. You have to really think about the whole system.
Exactly.
So with that in mind, let's talk about design goals and some of the key variables that come into play when you're designing a fracture treatment. And our sources connect this back to Darcy's law and something called equivalent well bore radius. Can you explain that a bit more?
Sure. So Darcy's law, like we talked about, describes how fluids flow through porous media. In a typical undamaged well, the flow is radial. So, it's like moving inwards from all directions towards the wellbore. But when you introduce a fracture, that pattern changes. Now you have fluid flowing mostly along the fracture towards the well. So this concept of equivalent wellbore radius, or RE, is a way to simplify that.
Okay.
It's basically the radius of a well that would have the same productivity as the fractured well, but without the fracture.
So it's like an imaginary well.
Right, exactly.
Okay.
But it helps engineers, quickly understand how effective a fracture is.
And how does this equivalent wellbore radius connect to the actual physical characteristics of the fracture, like its length and conductivity?
Well, that's where the dimensionless fracture conductivity comes in, CFD.
Okay.
This is a ratio that compares the conductivity of the fracture, KFW, to the ability of the reservoir to deliver fluids to the fracture. So the formula is CFD equals KFW over K times XF, where K is the reservoir permeability, and XF is the fracture half-length. So in the end, the main design targets are fracture half-length and fracture conductivity.
Right.
And their relationship is defined by this dimensionless conductivity. And there's this interesting thing, for a fixed amount of proppant, the maximum production increase tends to occur when CFD is between 1 and 2.
Oh, interesting.
So you have this sweet spot, right, where the fracture is long enough to reach a large volume of the reservoir, but it's also conductive enough to efficiently transport those fluids back to the well.
So Ra is how we describe the potential increase in productivity from the fracture. But how do we actually assess that increase? Like, how do we measure it?
Well, one way is to use the folds of increase, or FOI.
Yeah.
It's basically the ratio of the well's production after fracturing to the production before fracturing.
Okay, so it's like how many times better is it producing?
Exactly. And the equivalent wellbore radius, which we know is related to XF and CFD, can be used to calculate that FOI. There are charts and equations that directly relate these parameters, so we can actually predict how much of a production boost we'll get after the treatment.
But of course, the real world is never as neat and tidy as our models and equations, right? What are some things that can complicate things and make the actual production different from what we predict?
You're right. There are definitely a few things. For example, we have what's called non-Darcy flow, which is basically turbulent flow. It can happen when the fluid's moving really fast inside the fracture, and that can cause extra pressure drop and reduce the effective conductivity.
Okay.
Then there are transient flow regimes, which are the initial flow periods after you put the well on production. They don't always behave like steady-state flow. And if the reservoir has multiple layers with different permeabilities, the interaction with the fracture can be really complicated.
Right.
And lastly, if you have natural fractures, those can create what we call horizontal permeability anisotropy. That means the permeability is different in different directions, which can definitely mess with the flow patterns.
Okay, so those are some of the challenges in predicting real-world performance. Now let's talk about the actual equations that govern this process. Our sources highlight the material balance equation as a key one. Can you tell us more about what that tells us?
Yeah, the material balance equation is pretty fundamental. It basically says that all the fluid we pump into the well during fracturing has to go somewhere.
Okay.
Some of it leaks off into the rock, and the rest stays in the fracture. So we can write that as VI equals VLP plus VF, where VI is the total volume injected, VLP is the volume lost to the formation, and V is the volume of the fracture.
So it's a simple idea. Everything has to add up.
Exactly. It's like accounting for the fluids.
Right. And how do you actually calculate each of those volumes?
Well, the injected volume, V, that's pretty easy. It's just the injection rate, key, multiplied by the pumping time, TP. The fracture volume, VF, can be thought of as the product of the fracture height, HF, the average fracture width, W bar, the fracture half length, L, and an efficiency factor, ATEF, which takes into account that not all the fluid actually goes into creating the fracture.
Right.
The volume lost to the formation, VLP, is a bit trickier to calculate precisely, but there are equations that approximate it. Those take into account the fluid loss coefficient, CL, the height of the zone where fluid loss is happening, HL, the pumping time, TP, and a term for what we call spurt loss, which is a really quick initial loss of fluid.
So it's all about understanding where the fluid is going.
Precisely.
Our sources mention that there's like a typical average fracture width you see in these treatments. What is that?
Yeah, in low to medium permeability formations, you typically end up with an average fracture width of about 0.25 inches.
Okay.
But, that can vary by, 50% or so, depending on the rock, the fluid, and the stresses.
Right, of course.
But knowing that, you can then see how things like the fracture height, HF, and the fluid loss coefficient, CL, will affect how far the fracture extends.
Okay.
Like if you double the fracture height, you'll probably end up with a fracture that's about half as long. And if you double the fluid loss coefficient, the length might decrease by something like 20%.
Oh, okay.
But again, these are just rough guidelines. In reality, it can be much more complex.
Right, especially if you have a lot of fluid loss.
Yeah.
Now, we've talked about fracture height a bit. What actually controls how tall these fractures get?
So we have two important parameters here.
Okay.
The first is the actual height of the fracture, HF. Yeah. The second is the height of the zone where most of the fluid loss is happening, which we call HL. Now, HL is mostly controlled by the natural variation in porosity and permeability in the different layers of the rock.
Okay.
But the actual fracture height, HF, that's mostly controlled by the stresses in the rock.
Okay, the stresses.
Yeah. Specifically, it's the differences in the minimum horizontal stress between the pay zone, where we want the oil and gas, and the layers above and below it, which are often like shales. These layers act like barriers.
I see.
And the difference in stress between those layers, we represent that as delta sigma.
Delta sigma.
Yeah. So the ratio of the net pressure inside the fracture, net, to that stress difference, delta sigma, that ratio is what really determines if and how much the fracture will grow vertically.
So how does that ratio, net over delta sigma, actually affect things?
Well, if the net pressure is much smaller than the stress difference, like less than half of delta sigma, then the fracture is pretty much confined to the pay zone. Those stronger layers above and below keep it contained.
So it can't really grow upwards or downwards much.
Exactly. But if the net pressure gets much higher than the stress difference, then the fracture can break through those barriers and grow vertically pretty much unrestrained. You get a more complex fracture geometry that can extend way beyond the zone you're targeting.
And I imagine that's not ideal.
It can be problematic. The most challenging situation is when the net pressure is about the same as the stress difference. In those cases, even small changes in pressure can cause big changes in fracture height. Plus, the pressure drop as the fluid flows vertically in the fracture starts to matter more, and that makes it tougher to predict the final height.
So it gets pretty complicated.
Yeah, the interaction between the stresses and the fluid pressure is pretty complex.
And then, obviously, fracture width is critical, too. I mean, you need that width to get the proppant in there and keep the fracture open, right?
Right. Fracture width is super important for achieving good conductivity, or KFW. Ideally, you want a nice wide connection between the well bore and the propped part of the fracture.
Makes sense.
And the principles of fluid mechanics are what really determine that width. Specifically, the injection rate, key, and the viscosity of the fluid, mu. Those are the two main things we can control at the surface. And they directly affect the net pressure inside the fracture, which in turn affects the width. Higher net pressure generally means a wider fracture. These fluid properties also affect how well the proppant is transported and how much fluid leaks off into the formation.
I see.
It's interesting, though, pumping at higher rates can actually reduce the total fluid loss because there's less time for the fluid to leak off.
That's counterintuitive.
Yeah, it is. But that's how it works.
So you have to really balance these different factors.
You do.
Now, speaking of the fluids, what about material selection? How do you choose the right fluid and the right proppant for a specific job?
That's a critical part of the process.
Yep.
For the fluid, like we've been saying, viscosity is key.
Right.
You need enough viscosity to carry the proppant and open the fracture, but you don't want it so viscous that it creates huge pressure drops. And you need a clean fluid, without solids that could plug up the proppant pack. And of course, it has to be chemically compatible with the reservoir fluids and the rock. You don't want any weird reactions happening down there.
Right, of course.
You also have to consider the pressure and temperature down in the reservoir, because that can affect how the fluid behaves. And then there's the pumping pressure at the surface, the cost of the fluid, compatibility with other materials, and of course, safety and environmental regulations.
Wow, it's a lot to consider.
It is. And then for the proppant, the main thing is that it needs to maintain its permeability or conductivity under the stresses that will be on it once the fracture closes. And you also need to pick the right size. Larger proppant generally means better permeability, but it has to be able to fit through the perforations and be transported without getting stuck.
Right, so it can't be too big.
Right. And then finally, you have to figure out the right concentration of proppant to get the desired width and conductivity.
Okay, so it sounds like a lot goes into picking the right materials.
Definitely. It's not a one-size-fits-all situation.
Before we move on to the design process, let's talk a bit more about in-situ stress. We've talked about how it affects fracture height, but it seems like it plays a role in other aspects of fracturing as well, right?
Absolutely. The magnitude and orientation of the in-situ stresses, particularly the minimum horizontal stress, are like the fundamental control knobs for pretty much everything in hydraulic fracturing.
Okay.
First, it dictates the direction the fracture wants to grow. As we said before, fractures usually grow perpendicular to the minimum stress, and that's usually horizontal, so you get vertical fractures. But in some places, the vertical stress is actually the minimum stress, and then you can actually get horizontal fractures.
Wow.
Second, like we discussed, the difference in stress between the pay zone and the surrounding layers controls how much the fracture can grow vertically.
Right.
And third, the absolute magnitude of the stress directly impacts the equipment you need and the pressure you have to pump at.
Okay.
To create the fracture, the pressure downhole has to be higher than the minimum horizontal stress. That means you need powerful pumps at the surface to generate that pressure. And after the treatment, when the well is shut in, the closure stress, which is basically the minimum horizontal stress, acts to close the fracture. So if that closure stress is too high, it can crush weaker proppant.
So you're basically fighting against the earth itself.
In a way, yeah. So you have to choose a proppant that can withstand those forces to maintain the conductivity.
So how do you even begin to estimate what those stresses are?
Well, there's a simple equation that's often used as a starting point.
Okay.
It goes like this. Sigma H, which is the minimum horizontal stress, is approximately equal to co times the quantity sigma V minus PR plus T.
Okay, so break that down for me.
Sure. Co is a coefficient that depends on the elastic properties of the rock. Sigma V is the vertical stress, which is mainly caused by the weight of the rock layers above. Pre-R is the pore pressure, which is the pressure of the fluids in the rock pores. And T accounts for any tectonic stresses, the large-scale forces in the Earth's crust.
I see.
This equation can give you a rough idea, but for a real design, you usually need more accurate measurements or sophisticated models.
Makes sense.
You don't want to base a multi-million-dollar operation on a rough estimate.
So we have the reservoir engineers telling us what they want to achieve in terms of production. How do we, as engineers, design a fracturing treatment to actually meet those goals?
That's the heart of the design process.
Right.
We need to figure out what type and how much fluid to use, what kind of proppant, how much what size, how fast to pump it, and for how long. All to create a fracture with the right dimensions and conductivity to get the most out of that reservoir.
So there are a lot of moving parts.
A lot, yeah.
Let's break down some of the key considerations, starting with fluid and proppant selection.
Okay, so for fluids, viscosity is crucial, right?
Right.
Like we said, you need enough viscosity to transport the proppant and create the fracture width.
Yeah.
But if it's too viscous, it can create a lot of friction and pressure drops, making it harder to pump. And it has to be clean. Any debris or solid particles in the fluid can clog the proppant pack and reduce its conductivity.
So it's a balancing act.
It is.
Right.
And, of course, it has to be compatible with reservoir fluids and the rock itself. No chemical reactions or damage. And then you have to consider its performance at high pressure and temperature, the pumping pressure you'll need at the surface, the cost of the fluid, compatibility with other materials like the proppant, and, of course, all the safety and environmental regulations.
Right, because we don't want any accidents or contamination.
Exactly.
So a lot goes into choosing the fluid. What about the proppant?
For the proppant, the main thing is its ability to maintain its permeability, its conductivity, under the closure stress. Remember, that's the stress pushing on the proppant pack after the fracture closes. You don't want the proppant to get crushed.
Right.
So its strength is important. And then the size is crucial. Larger proppant means better flow, but it has to be able to get through the perforations and flow through the fracture without getting stuck. So there's this trade-off between conductivity and the ability to get the proppant where you need it. And finally, you have to decide on the proppant concentration. That will determine the propped width and the overall conductivity of the fracture.
So you're basically engineering the permeability of the fracture.
Exactly.
Now, what about the pad volume?
All right, welcome back to the deep dive. We talk a lot about energy tech on this show. Hydraulic fracturing is one of those things that's kind of, well, out of sight and out of mind. But today we're going to really try to understand the nuts and bolts, the fundamental physics of how it works. This is a pretty dense topic, but we're going to break it down together. Absolutely. We've got a ton of sources to help us do that. I think the goal here is to go beyond just the surface level stuff and look at the real core mechanical principles at play.
Right. So let's take a step back and look at our source material. We see that hydraulic fracturing isn't just like one mechanical process, right? It's a combination of like 4 different but totally intertwined fields.
Yeah, I mean, you've got your classic fluid mechanics, obviously, how those fracturing fluids move and behave inside the fracture itself.
Right. And then there's the rock itself, the formation. So that's where solid mechanics comes in, understanding how that rock deforms under all that pressure and eventually cracks. And then we go even deeper, right? Down to the tip of that growing crack, the fracture. That's fracture mechanics, understanding how the rock breaks and that fracture extends.
And we can't forget about the temperature difference, right? The fluid being pumped down is usually a lot cooler than the rock itself. So thermal mechanics comes in to explain how that heat exchange works.
Exactly. And the big takeaway here is that it's not just these 4 separate things happening. They're all linked. I mean, they're coupled and they all affect each other in ways that can get pretty complex.
Right. And that complexity is where the models come in, right? Like, how do engineers actually make sense of all this?
Yeah. Our sources point out like 3 main types of models. You've got the physical models, basically like scaled down lab experiments.
So like a MIDI version of what's happening downhole.
Exactly. Right? It's pretty straightforward. You pump fluid through a little rock sample and see what happens. The problem is they're super expensive, and it's tough to scale those tiny results up to a real-world fracture thousands of feet underground.
Right. Then you've got the empirical models, which are all about data. I mean, they don't even try to explain the physics. They just look at past results and try to find patterns.
Exactly. If you've got a bunch of data from wells in a certain area, like the treatment parameters and the production results, then you can use that data to predict what might happen with a new well in the same area. The cool thing is there's no scaling issue. But the downside is it doesn't work so well when you try to apply it to a totally different geological setting.
Right. And that brings us to the analytical or mechanistic models. These are all about using math and equations to actually describe the physics.
Exactly. It's like if you know the rules of physics, then you can, in theory, predict how a ball will fly, even if you've never thrown it at that exact angle before.
Right. So the equations are based on fundamental laws, like conservation of mass, how the rock deforms under stress, all that stuff. The advantage is you can, in theory, extrapolate beyond your data, but...
But there's always a but.
Right. But you have to simplify things to make the math work.
Exactly. Assuming the rock is perfectly uniform, the same everywhere, that kind of thing. But we know the subsurface is crazy complex, right? Different layers, natural fractures, all sorts of variations.
Okay, so the models themselves can get really complicated, and that's where the simulators come in.
Right. The equations for hydraulic fracturing are so complex, especially if you want to be realistic, that you need computers to solve them. It's all about finding approximate solutions.
So there's a trade-off, right? Like, more general models are potentially more accurate, but sometimes a simplified analytical solution gives you a better understanding of how the key factors relate to each other.
Exactly. Those cause and effect relationships, it's harder to see those in a huge, complex numerical model.
Now, before we jump into the specific models, why are we even doing all this? Why do we care about modeling hydraulic fracturing?
Well, for one, it's about money. It's about optimizing those treatments to get the most bang for your buck. I mean, figuring out the best size, the best design to maximize the return on investment.
Right. It's also critical for designing the pumping schedule, right? Figuring out the right rates, volumes, and the order of those fluids being pumped down.
Absolutely. And the models also allow us to visualize the fracture, like what shape will it be, how big will it get, and importantly, where will all that proppant end up?
The proppant being those little particles that keep the fracture open, right?
Exactly. And finally, the models help us evaluate a treatment after the fact. Did we achieve what we wanted? We can compare the predictions with the actual production results.
So it's all about understanding, like, how much fluid, how much proppant do we need to get the fracture we want? Or vice versa, working backwards from a desired outcome.
Exactly.
Okay, let's get into some specifics. Let's start with the PKN and KGD models. Now, both of these are best for situations where the fracture is pretty much contained within a layer. It's not growing vertically too much.
Yeah. But they go about simplifying that 3D problem into a 2D one in different ways.
Right. It's all about plane strain.
Right. Yeah. So the KGD model, that's Kristjanovich and Zheltov, it assumes plane strain in the horizontal direction. Basically, it's like each horizontal slice of that fracture is acting on its own, and it's basically the same as the slices above and below it. This model is good when the fracture is taller than it is long, or if there's a lot of slip at the boundaries of the pay zone. It really focuses on the fluid flow, the pressure gradients, and the effects at the fracture tip.
And the PKN, Perkins and Kern, that assumes plane strain vertically.
Right. So in this case, each vertical slice is acting independently. It's good when the fracture is much longer than it is tall, like a long crack. This one doesn't really focus on the tip details, but looks more at the fluid flow and pressure changes along the length of the fracture.
And these different approaches lead to different sets of equations.
Right. For the KGD, for instance, equations 625 and 626 tell you how the pressure changes along the fracture, how that gradient is related to the fluid viscosity and the flow rate. Equation 627 is interesting. It's called Baron-Blatt's tip condition, which basically says the tip of the fracture has to close smoothly. Then 628 through 632, they give you the fracture shape, the width profile, the total length, the width at the wellbore, with or without leak-off.
And for the PKN, we have 6.9, which, like in the KGD model, links the pressure drop to viscosity and flow rate. Equation 611 gives you the net pressure. From there, 612 helps you get the fracture width at any point, and 613 is specific for the width at the wellbore.
And a fun fact, the PKN model predicts that the average width of the fracture is usually about 80% of the width right at the wellbore.
So what about leak-off, that fluid leaking into the formation?
Yeah, that's huge. The PKN model uses Nordgren's numerical solution, which involves this dimensionless time, TD, defined by equation 624. It's more about the leak-off coefficient itself than the actual time. And since it's numerical, you don't get a neat equation for everything. But there are some good approximations when the fluid efficiency is really high, meaning little leak-off, or really low, meaning a lot of leak-off.
And those approximations, they give you some practical rules of thumb. Like with lots of leak-off, the fracture length is mostly controlled by how much fluid you're pumping in versus how much is leaking out. Like the fracture's just growing enough to accommodate the escaping fluid.
Yeah, that's a good way to think about it. And remember, the PKN model works best when the fracture is at least 3 times longer than it is tall.
Okay, so those models work great for fractures that stay within a layer. But what happens when they start growing vertically, breaking out of those confining layers?
Then you need models that can handle height growth. There are 3 main categories: general 3D, planar 3D, and pseudo 3D, which is usually called P3D.
General 3D sounds super comprehensive.
It is. It doesn't make any assumptions about the fracture's shape or orientation. It can handle all sorts of complex situations, like when the well is drilled at an angle or the perforations are in a specific pattern. But the downside is it's computationally crazy expensive. It's mostly used for research, not really practical for everyday field applications.
Okay, so planar 3D and pseudo 3D, what's the difference?
Planar 3D does a full 2D calculation of the fluid flow, but then couples it with a 3D representation of the rock deformation. P3D, on the other hand, simplifies things. It uses approximations for either the coupling or the rock elasticity.
And within P3D, there's lumped models and cell-based models.
Right. The lumped ones, sometimes called elliptical models, they basically assume the vertical cross-section of the fracture looks like 2 half-ellipses stuck together. They then use a spatial averaging technique to make the equations easier to solve. It's fast, but it relies on that elliptical shape assumption.
Right. And there are those gamma coefficients that pop up in these equations.
Yeah, those can be a bit tricky to determine, but if you have them, the lumped models are really fast and could be used for real-time applications.
Okay. And cell-based models?
They divide the fracture length into these little segments or cells. They don't assume a specific shape, but they do usually assume plane strain at each cross-section, kind of like the PKN model. So they're good for long fractures. They also assume the fluid flow is mostly horizontal.
Right. And there's that equilibrium height assumption, right?
Yeah, that basically means the vertical growth is slow enough that you can ignore the vertical pressure gradients in the fluid. The pressure in a cross-section is mostly from the wellbore pressure and the weight of the fluid column. Equation 645 shows that. Then, 646 and 647 give you the vertical extent of the fracture tips based on the stress differences. Finally, 648 gives you the fracture width profile. These models often use pre-calculated tables of solutions to speed things up.
But that assumption of mainly horizontal flow seems like it could be a limitation.
It can be, yeah. Our sources point out that it might not always be accurate, especially for some complex fluid behaviors.
Right. And just to recap, what are the planar 3D models good for?
They're more accurate and complex. They do a full 2D calculation of the fluid flow and couple it with a 3D calculation of the rock deformation. So you get a much better picture of the interaction between the fluid and the rock.
But computationally, much more expensive, I imagine. And it's worth mentioning, how do we actually know what those fractures look like in the field?
Well, our sources mention microseismic monitoring and tilt meters. Microseisms are those tiny earthquakes caused by the fracturing, so by looking at where they occur, we can estimate the fracture size, the length and height. Tilt meters, they're super sensitive instruments on the surface that can detect tiny tilts in the ground caused by the fracture opening. That gives us information about the width and the overall shape.
Okay, so we've covered a lot of models, from simple to complex. Now, are there some underlying principles that apply to many of these models?
Absolutely. One is that the width of the fracture at any point depends on the net pressure acting to open it, the integral of the pressure over the whole area. Equation 630 kind of shows that. This also depends on the rock's elastic properties, which we often assume are the same throughout the rock for simplicity.
Makes sense. Higher pressure, wider fracture?
Yeah.
What about how that fracture actually grows and changes shape?
That comes down to fracture mechanics, specifically LEFM, linear elastic fracture mechanics. The idea is the fracture will grow when the stress at the tip exceeds the rock's fracture toughness, which is basically its resistance to breaking. Equation 6.3 relates the fracture toughness to the energy needed to create new fracture surface.
So the rock's strength is a big factor in how the fracture grows. And of course, we have to consider the fluid itself.
Right. The fluid flow is governed by conservation of mass, which means the amount of fluid in a section can only change if fluid flows in or out, leaks off, or the volume of that section changes. Equations 638 and 639 show that. Then there's conservation of momentum, which is basically Newton's second law applied to fluids. The forces acting on the fluid, like pressure, viscosity, and gravity, determine its acceleration. Equations 640 and 641 show that.
And we need a way to relate the stress in the fluid to its flow rate.
Yeah, that's the constitutive law. Because fractures are thin, we use the lubrication approximation, which assumes the flow is mainly along the length and width, not much perpendicular to the walls. For Newtonian fluids, this leads to simplified equations like 642 and 643.
Now, one thing that seems super important is leak-off, like accurately estimating how much fluid escapes into the formation.
It's absolutely crucial. You can't design a treatment without understanding leak-off. We often do minifrac treatments just to measure the leak-off coefficient.
Right. And Carter's equation, way back in 1957, equation 614, that's still the basis for a lot of leak-off calculations. It considers three main processes: the reservoir fluids being compressed and displaced, the filtrate invading the formation, and the filter cake building up on the fracture walls.
Right. And Williams divided the leak-off process into 3 time periods. First, there's this initial spurt loss before the filter cake forms, then the period where the filter cake is building up, and then finally the dynamic leak-off where the filter cake is stable.
Okay, let's dive into those 3 processes. First, the filter cake.
So, the rate of fluid loss through that cake is proportional to 1 over the square root of time, equation 680. That gives us the fluid loss coefficient, CW, in equation 682. Then, the total volume of fluid loss, VW, is in equation 683, which originally included a spurt volume, SP, but a more refined approach, equation 684, considers a spurt time, TSP, before that square root of time behavior kicks in.
And there's the filtrate zone, that area invaded by the fluid.
Right. Assuming constant pressure drop, complete displacement of the original fluids, and incompressible fluid and rock, we get equation 685 for the leak-off rate. Integrating that and making an assumption about the invaded zone length, equation 686, we get the total leak-off volume, equation 687, and that introduces the viscosity control leak-off coefficient, CV, in equation 688.
And the third process, what's happening in the uninvaded reservoir?
Right. Here we assume compressible flow and a slow-moving fluid front. That gives us equation 690 for the leak-off rate and the compressibility control leak-off coefficient, CC, in equation 691.
Now, all 3 of those happen at the same time. How do we combine them?
The key is that the leak-off rate has to be the same at the fracture face for all 3 processes, and the pressure drops across all 3 zones have to add up to the total pressure difference. That's equation 694. That gives us a combined leak-off coefficient C in equation 696.
And our sources talk about how to extend this to multiple fluids.
Yeah, Satari and others showed that for multiple fluids, you can replace CV with an equivalent term, equation 697, that considers the average viscosity and permeability of all the leaked fluids. Similarly, CW can be replaced by an equivalent value, equation 698, that accounts for how each fluid contributes to the filter cake. Equation 699 even factors in the gel concentration.
And pressure also affects these coefficients.
Right. Equations 6100 and 6101 show how those coefficients change as the pressure difference changes. And there are even more complex things like pressure-sensitive leak-off, where the rock's permeability itself changes with pressure, and poroelastic effects.
Okay, leak-off is complex. Now, let's talk about proppant. What happens when we pump those little particles into the fracture?
3 main things to think about: how proppant affects the fluid's flow, the convection currents that can happen, and how the proppant actually gets transported and placed.
Let's start with the fluid flow.
Adding proppant usually makes the fluid more viscous. For Newtonian fluids, there are correlations for that. For non-Newtonian fluids, which are common in fracturing, it's trickier, but Nolte showed you can adapt the Newtonian relationships using the flow behavior index, N.
What about those convection currents?
They happen because the proppant slurry is denser than the base fluid, so it tends to sink. This creates vertical flow patterns. Both theoretical work and experiments have shown that these currents are important in how proppant gets distributed.
And getting the proppant placed correctly is key.
Absolutely. Gravity makes those particles settle. Stokes' law, equation 6106, gives you a theoretical settling velocity for a single particle in a Newtonian fluid. But of course, it's way more complicated in reality. We've got non-Newtonian fluids, high concentrations, and the fracture walls affecting the flow. This leads to hindered settling, where the particles get in each other's way, and clustered settling, where they clump together. Novotny's correlation, equations 6107 and 6108, accounts for hindered settling. And for power law fluids, we use a generalized Stokes law, equation 6109.
So the fluid properties, the density difference, and the settling behavior, they all affect where that proppant ends up.
Right. It's a balancing act.
Now let's talk about heat transfer. The fluid we pump is usually much colder than the reservoir. What happens there?
Heat exchange, obviously. The fluid warms up and the rock cools down. The fracture is so thin that we usually simplify it to a 1D problem, heat flowing perpendicular to the walls.
Right. And there are some refinements to those basic models.
Yeah, like Meyer's work with the convective heat transfer coefficient, which accounts for the resistance to heat flow at the fluid-rock interface. He also used the Nusselt number to calculate that coefficient.
And then there are numerical simulators that can handle even more complexity.
Exactly, like variable pump rates, shut-in effects, all that. And there's a really efficient algorithm for these calculations, detailed in Sidebar 6i. It's stable and fast, and it matches the results from more complex simulators pretty well. You can see that in Sidebar 6J and Figure 612.
So understanding heat transfer is important because it affects the fluid properties and reaction rates, especially in acid fracturing.
Absolutely.
Now let's zoom in on the fracture tip, that leading edge where the fluid is pushing into the rock.
There are 4 main things to consider there. The actual rock failure and opening, the possibility of a disturbed zone ahead of the tip, a fluid lag zone where the fluid hasn't fully penetrated, and a disturbed zone along the fracture face.
Starting with the failure and opening, LEFM is back.
Yeah, linear elastic fracture mechanics. It tells you when a crack will grow based on the stress and the rock's fracture toughness. Equation 6.3 shows the relationship between fracture toughness and the energy needed to create new surface.
Then there's that fluid lag zone.
Right, where the fluid pressure is lower than the closure stress. That clamps the tip shut a bit, reducing the stress intensity. To account for this, we use an effective fracture toughness, equations 6.113 to 6.115.
And dalatency, the rock expanding near the tip.
Yeah, that can increase the fluid pressure and stress locally. Equation 6.116 is a modified fracture toughness that accounts for this.
And our sources mention calibrating that effective fracture toughness using field data.
Yeah, Schley-Pobersky and his colleagues came up with a method using the shut-in pressure, ISIP, and the closure stress. Equation 6.117 gives you the field scale effective fracture toughness.
Now let's shift to the near wellbore area. Are there any special considerations there?
Definitely. High friction losses near the wellbore are a big problem, especially in deviated wells or when the perforations aren't ideal. This can lead to higher pressures and screenouts. Several things contribute to this, like poor communication between the wellbore and the fracture, tortuosity, misaligned perforations, pinching, and even multiple fractures.
Let's unpack some of those, starting with perforation friction.
If the perforations are too small, too few, or have rough edges, they create a pressure drop. Equation 6.120 estimates that considering factors like flow rate, density, and a discharge coefficient. And erosion can change this over time. Figure 6.14 shows that. Figure 6.15 shows how including perforation friction in a model can affect the predicted pressure.
And tortuosity, where the fracture doesn't go straight.
Right, as in Figure 6.16. This makes the flow path longer, increasing pressure drop and potentially causing pinching. Increasing fluid viscosity and pumping a larger pad can help with this.
And wellbore pinching, that sounds bad.
It is. If the perforations aren't aligned to the fracture plane, it creates pinch points. Figure 6.17. The stress field can also cause pinching, Figure 6.18. Figure 6.19 shows how this gets worse with higher pressure. Injecting small slugs of low viscosity fluid can sometimes help.
Okay, near wellbore effects are complex. Now what about acid fracturing? How is that different?
Acid fracturing brings in chemical reactions between the acid and the rock, usually limestone or dolomite.
And those reactions create the conductive pathway, right? Instead of proppant, it's the etching that keep the fracture open.
Exactly. Equation 6.126 gives you the etched width. But unlike a prop fracture, the etching isn't uniform. This creates channels and pillars, and the conductivity depends on those, not just the average width. Empirical equations like Nearroad and Crux, equation 6.127 to 6.130, estimate the conductivity.
And those reactions release heat.
They do, yeah. It's exothermic. Equation 6.131 relates the acid concentration change to the temperature change. Modeling this heat transfer is important because the reaction rates depend on temperature.
And how are those reaction rates modeled?
It's complicated. The Arrhenius equation, equation 6.133, shows how the reaction rate constant depends on temperature. Equation 6.134 is a simplified expression for the acid consumption rate, using a temperature-dependent rate constant, equation 6.135.
But the acid has to get to the rock surface to react.
Right, that's mass transfer. In a stagnant fluid, it's diffusion, Fick's law, equation 6.136. Williams modified that to include leak-off, equation 6.137. But in a flowing fluid, convection is dominant. Equation 6.138 describes that, using the mass transfer coefficient, equation 6.139, and the Sherwood number, equation 6.140.
So the acid concentration at the surface is a balance between how fast it gets there and how fast it reacts.
Right. Equation 6.143 shows that balance. We can have mass transfer limited reactions, equation 6144, or kinetics limited reactions, equation 6145.
And how does this all fit into the fracture geometry models?
You have to track the fluids, account for the etching length receding, and modify the pressure-width relationship, equation 6146.
Now, what about multiple fractures?
That adds the complexity of fluid partitioning. We need models that can handle multiple fractures growing at the same time. Equations 6147 and 6148 show the coupling conditions. The total flow rate has to be split between the fractures, and the pressure at a reference point has to be the same. Figure 621 shows a simulation of a multi-layer treatment, and Figure 622 shows some of the complex effects that can happen, like screen-outs and cross-flow.
Sounds challenging.
It is. And our sources say that unless the wellbore is very well aligned with the minimum stress, those multiple fractures probably won't connect.
Now, how do we actually generate those pump schedules, the instructions for the treatment?
It can be pretty involved. For simple cases, we can use analytical solutions like the ones in Sidebar 6L. But for complex cases, we use numerical simulators in inverse mode. Instead of inputting the schedule, we input the desired outcome, like a propped length and proppant concentration. The simulator then figures out the schedule that's most likely to achieve that.
So it's like the simulator designs the treatment.
Kind of. It's iterative. It starts with an estimate, then adjusts the pumping based on leak-off and proppant concentration. The whole process might need to be repeated a few times.
Sidebar 6L also has some approximate methods for proppant schedule design.
Yeah, Nolte's work, those are good starting points, especially for routine treatments. Equations 6L4 to 6L8 and figure 6L1 show those.
Okay, lastly, pressure history matching.
That's about using the pressure data recorded during the treatment to figure out things about the formation that we might not know precisely, like the stresses, the permeability, the elastic properties.
So you're trying to find the inputs to the model that will match the recorded pressure.
Right. It's iterative. You start with some guesses, run the simulation, compare the pressures, adjust the inputs, and repeat. Equations 6M1 to 6M4 describe that process. Figure 624 shows an example of a pressure match, and Table 6.1 lists some of the parameters you can estimate. It's important to use other data like logs and to choose the right model to avoid getting multiple solutions that all look good but might not be accurate.
So pressure history matching is a powerful tool, but you have to use it carefully. Well, this has been a seriously deep dive into hydraulic fracturing.
It's amazing how many different things are happening down there.
And the models are how we try to make sense of it all.
Exactly.
And the models are constantly evolving, getting more realistic and accurate.
Right. So what do you think, listener? What's the biggest challenge in taking this technology even further and making sure it's done responsibly? We encourage you to check out the sources and keep digging into this. Thanks for joining us on this deep dive.
All right. Welcome back, everyone, for another deep dive. And today, we're going to be tackling something really at the heart of how we access energy, hydraulic fracturing fluids. Now, you sent us over a whole bunch of material on this. It's really quite a deep well of information. You know, we've got stuff here about the fundamental chemistry going on, all the way down to the specifics of the proppants being used.
Yeah, fascinating stuff.
So what we're going to try to do today is really pull out that essential knowledge, the core insights about what actually makes fracking work. You know, without getting too bogged down in the really, really technical details.
Absolutely, yeah.
And we'll be looking at both the chemical makeup of these fluids, you know, those fascinating concoctions that get pumped down there, as well as those tiny but mighty particles we call proppants.
Right.
And believe me, there are some really surprising facts waiting to be uncovered here.
Yeah, when we think about fracturing fluids, you know, our first thought might just be, you know, about cracking rock. Mm-hmm. But when you look at the information you sent over, the reality is far more complex.
Yeah.
You know, yes, creating fractures is a primary goal, and keeping them open using proppant, of course. But the key to success really boils down to viscosity, you know, how resistant that fluid is to flow. Mm-hmm. Think about it like trying to suspend sand in plain water versus like a thick syrup.
Right.
The more viscous fluid does a much, much better job of holding those particles in place.
Exactly.
Yeah.
But here's where it gets really interesting, because it's a successful fracking operation. It's not just about making a really thick fluid. Your materials highlight a whole range of other essential properties that these fluids need to have.
Right.
And, you know, we're talking about things like the ability to break down rapidly and cleanly after the treatment is done. So we don't leave a bunch of sticky residue down in the formation. Mm-hmm. Then there's effective fluid loss control. making sure the fluid isn't just seeping into the surrounding rock, instead of extending the fracture network, and low friction pressure during pumping.
Yeah.
Vital for, making the process as efficient as possible energy-wise.
Right.
And of course, it all needs to be cost-effective at the end of the day.
Right.
It's this amazing balancing act of so many different requirements.
It truly is. And to really grasp where we are with these fluids today, it helps to take a quick look back at their history, which your sources nicely lay out.
Right.
Initially, way back when, the industry relied heavily on oil-based fluids. But the late 1950s marked a pretty significant shift. Water-based fluids started gaining popularity, and the key ingredient for thickening those was good old gar gum.
Gar gum. It almost sounds like something you'd find in the, baking aisle of the grocery store.
Right. Yeah.
But it's playing a seriously powerful role in this whole industrial process. And then a major turning point in 1969, right? The first cross-linked gar treatment.
Yeah.
That sounds like a real game changer.
Yeah, it was indeed a significant advancement. And if we fast forward to the present day, the information you've shared indicates that these water-based gels, primarily those thickened with gar or its close relative, hydroxypropyl guar, they now dominate the field, making up over 65% of all treatments.
Oh, yeah.
You've got gelled oil and acid fracturing each account for a much, much smaller portion, about 5% each. And interestingly, a significant number of treatments, somewhere between 20% and 25%, also include energizing gas.
Okay.
And finally, we have those unsung heroes, the additives, which are absolutely crucial for tailoring the fluid to the specific conditions, deep underground.
Right.
We're talking extreme temperatures, challenging fluid loss scenarios, all of that.
So let's unpack this a bit, starting with the workhorse, water-based fluids. Your materials really emphasize their widespread use, and it's really thanks to that winning combination, right?
Yeah.
Low cost, high performance, and relatively straightforward handling.
Right.
But there's a hurdle to overcome here, isn't there? Temperature sensitivity.
Precisely. Simple polymer solutions, they work great at surface temperatures, but they have this tendency to thin out considerably as the temperature rises downhole. You could try to compensate by just adding more and more polymer. But as your sources point out, that quickly becomes way too expensive. It's just not practical.
Right.
So the ingenious solution here is cross-linking.
Cross-linking. Now, that's a term we hear all the time in this field. But what's the core idea behind it?
Think of individual strands of uncooked spaghetti.
Okay.
They slide past each other really easily. That's kind of like an uncross-linked polymer solution, providing some viscosity. But now imagine tying those spaghetti strands together at various points. Suddenly you've got this much more interconnected, this robust network, and that's essentially what cross-linking agents do at a molecular level.
Wow.
They create these connections between the long polymer chains, which significantly increases the effective molecular weight, without needing to use a huge amount of polymer overall. Your materials even include a graph, figure 7.1, that visually demonstrates this dramatic viscosity increase achieved through cross-linking, especially as those temperatures rise, compared to just adding more and more unlinked hydroxypropyl guar.
Yeah.
And the specifics, the nitty-gritty of that cross-linker chemistry, as your sources mention, are detailed a little bit later on.
I love that spaghetti analogy. It really makes it clear. So let's talk about gar gum itself. It's nature's contribution to this whole high-tech process. And it's derived from gar beans, which, according to your information, are mostly grown in Pakistan and India.
That's right.
So it's quite a journey from a simple bean to a complex fracturing fluid.
It is quite a process. And figure 7.2 in your materials gives you a nice visual overview of that whole journey from the plant pods to the final powdered product. And chemically, gar is a long-chain polysaccharide. Essentially, a long molecule made up of repeating sugar units, specifically mannose and galactose.
Right.
And when this powder is mixed with water, it really has this affinity for it. It wants to grab onto those water molecules. And the particles swell. They become associated with water molecules. They hydrate. And those long, tangled strands, they kind of unfold and extend into the solution. It's these overlapping and interacting strands that create the viscosity we've been talking about.
And our understanding of gar's molecular structure, it's actually evolved over time, hasn't it?
Yeah.
Initially, it was thought to be this neat repeating pattern of one galactose unit for every 2 mannose units.
Right. Figure 7.3 in your materials actually depicts that earlier, more simplified model. But more recent research indicates that that arrangement of those galactose side chains is likely more random. They may appear on 2 or even 3 consecutive mannose units sometimes.
Okay.
And even the ratio of mannose to galactose itself isn't a fixed 2.1. It can range from about 1.6.1 to 1.8.1. So, it highlights this key insight. And even seemingly well-understood natural materials, they can still hold some surprises at the molecular level. And that's why we're constantly refining our understanding.
It just goes to show, there's always more to learn.
Always.
And it's not a perfectly pure substance either, right? Your sources mentioned that GAR fluids can contain, a noticeable amount of insoluble residue.
Exactly. The processing of the GAR beans doesn't completely separate the desired GAR polymer from other plant materials that just don't dissolve in water.
Right.
And that can leave anywhere from 6% to 10% of this insoluble residue in the final fluid.
Okay, so to address some of these limitations, we have hydroxypropyl GAR, or HPG. It's like GAR, but with some key improvements.
Precisely. And figure 7.4 in your materials shows the repeating unit structure of HPG. It's created by chemically reacting GAR with propylene oxide. Essentially, you're adding hydroxypropyl groups to some of the OH groups on the GAR molecule. It seems like a small change, this chemical modification, but it has a couple of important benefits.
Okay.
Firstly, the additional processing and washing steps during HPG production, they remove more of that unwanted plant material. So the insoluble residue is reduced down to just 2% to 4%. And secondly, the addition of these hydroxypropyl groups makes HPG more thermally stable than unmodified GAR. So it's a better choice for those hotter wells with temperatures exceeding 300 degrees Fahrenheit.
It's fascinating how these, seemingly minor tweaks at the molecular level can have such a big impact in the real world. Now, there was a thought, I think, at some point that HPG was less damaging to the formation and the proppant pack compared to GAR. But your sources kind of suggest that might not necessarily be the case.
Yeah, that's what more recent studies are indicating. Despite that lower amount of insoluble residue, the overall degree of damage to the formation and proppant pack seems to be pretty similar between GAR and HPG.
Interesting.
It's a good reminder, really, that those initial assumptions, we need to rigorously test them, and verify them with further research.
Yeah, always good to keep testing those assumptions. Now, something interesting you mentioned, that hydroxypropyl modification. It makes HPG more soluble in alcohol, right? And that actually provides a pretty handy method for quality control.
It does.
You add methanol to a solution of the polymer. GAR will precipitate out of the solution, whereas HPG, with the standard level of substitution, will remain dissolved.
Exactly. And the simple test, as your sources note, it can even be used to, detect HPG that hasn't been sufficiently modified during the production process. So it's a good way to ensure quality.
So we're seeing this trend here, right? Take a base polymer and then tweak it chemically for specific applications. And next up, we've got carboxymethylhydroxypropyl GAR, or CMHPG. That's quite a mouthful.
It is. Think of it as a double derivatized GAR. It's got that hydroxypropyl functionality of HPG, but it also has these carboxymethyl groups attached to the polymer chain.
Okay.
And initially, CMHPG, it kind of found its niche in lower temperature wells where it could be effectively cross-linked with aluminum ions through those carboxy groups. Yeah. And this offered a more cost-effective option compared to using, more complex titanium or zirconium-based cross-linkers with HPG.
Right.
However, more recently, CMHPG has also been successfully cross-linked with zirconium ions to create fluids that actually exhibit even higher viscosity at elevated temperatures than standard HPG-based fluids.
Wow. So it's proving to be a rather versatile modified polymer.
So GAR and its various derivatives, they're the dominant players, but there are other polymers in the mix as well, right? Yeah. Cellulose derivatives, for example, hydroxyethyl cellulose, or HEC, and hydroxypropyl cellulose, or HPC, they get a mention in your sources, particularly for situations where a really clean fluid is the top priority.
Exactly. Figure 7-5 in your materials shows the repeating unit structure of HEC. And these polymers have a backbone made of glucose sugar units, which is similar to GAR's mannose backbone. But there's this crucial difference in the spatial arrangement of those hydroxyl nucleic groups. In GAR, they're on the same side of the sugar molecule, what we call a cis orientation.
Right.
But in HEC, they're on adjacent carbons, but on opposite sides, what we call a trans orientation.
Okay.
And this seemingly minor difference at the molecular level, it actually has this huge impact on how these polymers can be cross-linked. So the cis orientation in GAR makes it easier to cross-link with those common metal ions, whereas the trans orientation in HEC poses a bit more of a challenge.
Precisely. However, HEC can still be cross-linked, typically requiring a high pH around 10 to 12 using zirconium or even lanthanide compounds. And to make HEC cross-linkable under more moderate conditions, you can add a carboxymethyl group, creating carboxymethyl hydroxyethyl cellulose, or CMHEC. And this modification allows for cross-linking with a broader range of metal ions, including aluminum-3, titanium-4, and zirconium-4 at a more neutral pH range, around 4 to 6.
Okay, so moving beyond these modified natural polymers, we encounter xanthan gum.
Yeah.
And this is a biopolymer with some really unique properties.
Yes, xanthan gum, the repeating unit of which is shown in Figure 7.6, is a fascinating biopolymer. It's actually produced by the Xanthomonas campestris microorganism through fermentation. And unlike HPG solutions, which behave as Newtonian fluids at low shear rates, meaning their viscosity is relatively constant, regardless of how gently their stirred xanthan solutions exhibit what's called power law fluid behavior, even when the fluid is barely moving.
Okay.
And what's interesting about that is even when the fluid is barely moving, it still has this good ability to hold the proppant in place, unlike other fluids that might let the sand settle out quite quickly.
Right.
Studies have shown that it has superior sand suspension capabilities at these low shear rates, which you typically find in the fracture after pumping has stopped, compared to HPG. Now, it is currently more expensive and therefore less frequently used than GAR or cellulose derivatives.
Okay.
But its excellent sand suspension properties, they hint at this potential for increased use in the future.
Interesting.
And your sources also briefly mention scleroglucan. It's another biopolymer that boasts excellent proppant suspension. And quite remarkably, it doesn't even require a breaker to reduce its viscosity after the treatment. It degrades naturally over time.
Wow, that's pretty neat.
Yeah.
Okay, so we've covered those main players, those viscosity builders.
Mm-hmm.
But what about those other specialized properties we talked about at the very beginning? Friction reduction, for instance, during pumping.
Oh, that's absolutely crucial for efficient operations. Partially hydrolyzed polyacrylamide polymers are the key here. And even at very low concentrations, we're talking less than 10 pounds per 1,000 gallons of water. These polymers can significantly reduce that friction pressure as the water is pumped at those high rates downhole.
Mm-hmm.
And this translates directly into saving a considerable amount of energy and pumping horsepower.
Okay. And sometimes the fracturing fluid itself needs to be acidic, particularly when dealing with carbonate formations. So what thickeners are used in those cases?
When working with acid-based fracturing fluids, acrylamide copolymers are typically used to increase viscosity. However, a significant issue to avoid is the precipitation of acrylamide homopolymers, polymers made up of only acrylamide units. And this can happen in the presence of calcium ions, which are released in large quantities when hydrochloric acid reacts with limestone formations.
Mm-hmm.
So the copolymers used in acid fracturing are specifically designed with other chemical groups attached to that polymer backbone. Mm-hmm. And these modifications prevent the hydrolysis of the acrylamide groups, ensuring that the polymer remains soluble even in that calcium-rich environment of spent acid.
Right, so it can maintain viscosity even at those elevated temperatures.
Exactly.
It's all about, carefully tailoring that chemistry to the specific rock type and the reservoir conditions.
Precisely.
Now, we also have these intriguing polymer-free fluids that utilize viscoelastic surfactants, or VES.
Right.
And that sounds like a completely different approach to creating viscosity.
It is. It is a fundamentally different mechanism. So instead of relying on long polymer chains, VES fluids, as illustrated in Figure 7-7, they depend on the self-assembly of surfactant molecules. These are typically quaternary ammonium salts of a long-chain fatty acid. And these molecules have a hydrophilic or water-loving head and a hydrophobic or water-fearing tail. So when you add these to an aqueous solution, these molecules spontaneously arrange themselves into these spherical structures called micelles.
Okay, and we've seen diagrams of micelles before. They kind of look like tiny spheres with the water-living heads on the outside and the water-fearing tails kind of pointing inwards, creating this hydrophobic core.
Exactly, and you can see that in Figure 7-8.
But how do these microscopic structures create a viscous fluid? That's the question.
So in the presence of an optimal concentration of salts, usually potassium chloride or KCl or ammonium chloride, NH4Cl, these spherical micelles, they transition into these elongated rod-like shapes.
Okay.
And if the surfactant concentration in the fluid is high enough, typically above 1% by volume, these rod-like micelles, they start to associate and entangle with each other, forming this three-dimensional network. And it's this network of entangled rods that hinders the flow of the fluid, resulting in increased viscosity and even some elasticity.
So it's almost like those individual rods are acting like tiny little pieces of a larger structure that's all linked together.
Exactly. And interestingly, these associations are primarily electrostatic in nature, meaning that VES fluids are generally less sensitive to the history of the shear forces that are applied to them compared to traditional polymer-based gels. So if that network of micelles is temporarily disrupted by shear, it can quickly reform once that shearing force is removed. However, like polymer solutions, temperature does affect their performance. So the surfactant and sometimes the salt concentrations, they need to be carefully adjusted depending on what temperatures you're expecting downhole.
Right. So there's always the balancing act.
There is.
But the really unique and advantageous aspect of VES fluids, according to your sources, is their ability to clean themselves up after the fracturing treatment.
Absolutely. That micellar structure, it's inherently temporary and dynamic. It's readily disrupted by contact with hydrocarbons, which, after all, is the goal of the treatment, to produce oil and gas, and also by dilution with aqueous fluids like the formation water that's naturally present in the reservoir.
Okay.
So this means that as the well starts producing, the VES fluid naturally breaks down and loses its viscosity.
So you don't need those separate chemical breakers.
Exactly. And this residue-free cleanup, it's a significant advantage, leading to considerably less damage to the proppant pack and the fracture face. Retained permeability after using VES fluids is typically very high, often exceeding 95%. And furthermore, they can even be readily foamed with nitrogen gas without the need for additional foaming agents in the fluid.
It's like a self-cleaning oven in a way.
Right.
You know, it just kind of takes care of itself.
Yeah.
So VES fluids present this fascinating alternative, particularly in situations where ensuring that clean and unimpeded flow path after fracturing is paramount.
Yeah.
Now let's shift our focus to oil-based fracturing fluids.
Right.
You mentioned earlier that these were actually the first types of fluids used in the industry. So
yeah.
What led to that subsequent shift towards water-based systems?
Initially, oil-based fluids were favored because they were thought to be less likely to cause damage to hydrocarbon-bearing formations compared to water-based fluids.
Okay.
And their inherent viscosity also provided a natural advantage for proppant transport. However, they do come with some significant drawbacks.
Yeah.
They're generally more expensive than water-based fluids, and they're also more complex to handle operationally.
Right.
You know, posing some environmental and safety challenges. So as a result, their use today is largely restricted to formations that are known to be extremely sensitive to contact with water.
Okay, so they still have their niche.
They do.
And how are these oil-based fluids thickened? Because it's certainly not gar, gum, and oil, I would imagine.
No, definitely not. In the 1960s, a key method for increasing the viscosity of hydrocarbon fluids involved using aluminum salts of carboxylic acids. A common example being aluminum octote.
Okay.
And this approach, it improved the temperature stability of the gelled oil and its ability to carry proppant.
Right.
And then in the 1970s, aluminum phosphate ester salts emerged, and these offered further enhancements in terms of the temperature range over which the gel remains stable and the effectiveness of proppant transport. And surprisingly, aluminum phosphate ester chemistry continues to be the preferred method for gelling hydrocarbons for use in fracturing fluids, even today.
Wow, so it's stood the test of time.
It has, and both of these methods, they rely on what's described in your sources as an associative mechanism.
Okay, associative. What does that mean in the specific chemical context?
So figure 7-9 in your materials provides a proposed molecular structure, and essentially it involves these interactions between aluminum complexes and phosphate ester molecules.
Okay.
And this leads to the formation of these long chain-like polymeric structures. And it's these elongated structures that provide that viscosity to the oil-based fluid.
So it's kind of like they're linking up and forming these long chains.
Exactly. And the R groups that you see in that diagram, they represent hydrocarbon chains that must be soluble in the specific oil that's being gelled.
Okay.
And these soluble R groups, they essentially help to keep the aluminum phosphate ester polymer dissolved within the hydrocarbon fluid. Typically, these R groups, they contain anywhere from 1 to 18 carbon atoms, giving them a good chemical affinity for oils like kerosene and diesel fuel, which have similar ranges of carbon chain lengths in their molecules.
Okay.
However, crude oils are much more complex mixtures, and they can contain components like paraffins and asphaltenes, which might not be compatible with this particular gelling system.
Right.
So while many different types of crude oil can indeed be gelled using this chemistry, it's always a prudent step to perform a compatibility test beforehand.
Right. Just to make sure everything's going to play nicely together down there.
Exactly. To avoid any potential issues during the fracturing operation.
So it sounds like these oil-soluble R groups, they're creating this sort of oil-compatible shield around the more polar, the core containing the aluminum ions and the phosphate groups.
That's a very, very accurate way to visualize it.
Okay.
And because of this polar core, the presence of other polar species like water, acids, bases, or salts, they can actually affect the association between the aluminum ions and the phosphate ester groups.
Right.
And this can either lead to a strengthening of the gel structure or in some cases even cause it to break down. The viscosity of the gelled oil is typically controlled by carefully adjusting the relative amounts of the aluminum compound and the phosphate ester that are used in the mixture.
Right. So it's all about finding that sweet spot.
Exactly.
Now, to maintain sufficient viscosity at those high downhole temperatures, one approach is simply to increase the concentration of the polymer that's formed.
Right.
But that can lead to extremely high viscosities at the surface, making the fluid very difficult to pump down the well.
It can. So one clever technique that has been developed is to add some of those gelling materials on the fly as the hydrocarbon is being pumped downhole.
Okay.
And this allows the high viscosity to develop only as the fluid approaches the fracture zone, minimizing those pumping difficulties at the surface.
Right. So it's like a dilute reaction kind of thing.
Exactly. And another strategy involves carefully optimizing the chemical composition of the solution to really maximize the strength and the thermal stability of those associations between the aluminum and phosphate ester species.
Okay. Now, traditionally, these oil-based gels took quite a bit of time to fully form after mixing, didn't they?
Yeah, that's correct. The gelation process, it could typically take several hours to reach the desired viscosity.
Right.
But recent advancements in gelled oil chemistry have made true continuous mix systems a reality.
Wow.
By carefully selecting the specific aluminum source, adjusting that precise ratio of aluminum to phosphate ester, and even using a blend of different types of phosphate esters, they can achieve gel compositions that thicken very rapidly.
Yeah.
And this allows all the components to be added on the fly, as the hydrocarbon fluid is being pumped, with the gel forming while it's on its way down to the perforations in the wellbore.
So that eliminates the need for large-scale premixing operations and the logistical challenges and costs associated with disposing of any unused gelled oil after the job is complete.
Exactly. Increased efficiency and reduced waste.
Yeah, very significant improvements. Now let's move on to acid-based fracturing fluids. And this is kind of a different ballgame altogether, right? Focusing on chemically dissolving the rock to create conductive pathways.
Right. Acid fracturing, which primarily uses hydrochloric acid, HCl, is specifically employed in carbonate formations.
Okay.
Like limestone and dolomite. And the acid is injected at a pressure high enough to either create new fractures in the rock or to open up those existing natural fractures. And as the acidic fluid flows along those fractures, it chemically reacts with and dissolves portions of the rock face. And because this dissolution process tends to be somewhat uneven, preferential along certain paths, it creates this network of conductive channels that remain open even after the fracture closes and the pressure is released.
Okay.
And the overall effectiveness of the acid fracturing treatment is largely determined by by the length and the complexity of this etched fracture network.
Right.
Which in turn depends on factors like, the total volume of acid that's used, its chemical reaction rate with the rock, and how much of that acid leaks off into the surrounding formation instead of actually contributing to the fracture etching.
So in carbonate reservoirs, you often have this choice, right, between using acid to etch channels directly into the rock, or using a non-reactive fluid to create those fractures, and then propping them open with the solid proppant. So what are the key trade-offs there between those two approaches?
Operationally, acid fracturing offers a certain degree of simplicity because you don't have to handle or place those solid proppant materials.
Right.
So there's no risk of a proppant screen out during pumping, no proppant flowback issues during production, and no need for later cleanup of proppant from the wellbore.
Right.
However, acid itself is generally more expensive, on a per volume basis, compared to those non-reactive fracturing fluids. And that the major challenge with acid fracturing, as your sources clearly point out, lies in effectively controlling the loss of that reactive acid fluid into the surrounding porous rock matrix.
Yeah, fluid loss. It seems to be this recurring and significant challenge in all types of hydraulic fracturing.
Right.
But it's even more problematic when using acid, isn't it?
Absolutely. That continuous chemical erosion of the fracture faces by the flowing acid, it makes it very difficult to establish and maintain an effective filter cake. That low permeability layer of material that builds up on the fracture face and acts to block further fluid leak off.
Right.
Additionally, acid leak off tends to be very, very uneven, often leading to the formation of what are called wormholes. And these are enlarged, highly permeable channels that propagate away from the main fracture.
Right.
And this uneven leak off, it significantly increases the total surface area through which fluid can. Welcome back to the deep dive.
It's great to be here.
Today we're going deep underground.
Oh, yeah.
To explore something crucial to unlocking those energy resources we're always talking about.
Okay.
Hydraulic fracturing fluids.
Yeah.
Specifically, we're going to try to break down how scientists and engineers figure out what's actually going on in these complex mixtures.
Yeah, you shared a chapter with me called Performance of Fracture Materials.
Yeah.
And what we really want to do is sort of pull out the core knowledge for you.
Right.
Almost like a cheat sheet to understanding the science behind what goes into stimulating these wells.
Exactly. This chapter is dense. It's got so much expert information.
Yeah.
But that's what we're here for. We're going to be your guides, and we'll highlight the really fascinating stuff.
I like that.
Our deep dive today is all about understanding these fracturing fluids.
Right.
What goes into characterizing them, why it's so important, and the methods that are used.
And why should you, our listener, care about any of this? Well, if you're heading into a meeting in the energy sector, trying to grasp a new technical area, or simply curious about how things work, understanding how these fluids are analyzed gives you a foundational understanding. It's about understanding the essential properties that make these fluids effective, and sometimes their limitations.
Okay, so let's get into why this characterization is so vital.
Okay.
The chapter lays out 3 main reasons.
Okay.
The first is all about innovation.
Okay.
Developing those new and improved additives and complete fluid systems, and it comes down to performance and cost.
Precisely. Researchers are constantly refining those recipes, looking for that perfect balance of superior performance at an economical cost.
Right.
Characterization helps determine if the new ideas actually represent a step forward.
Makes sense. The second reason is really important for the engineers on the ground.
Yeah.
Characterization provides the data that powers those fracture design simulators. And these simulators are highly sophisticated software that help plan and really optimize every fracturing treatment.
Without accurate data on how these fluids behave under different conditions, those simulators couldn't make reliable predictions. So the lab work is directly linked to successful and efficient operations in the field.
And the third reason, which we're not going to go into too much detail today, is all about quality control.
Okay.
And this happens right before or even during a fracturing job in the field, making sure the fluids used meet the required standards.
Field tests might be a little less controlled.
Yeah.
But they offer a quick check on how the system's performing in real time.
So for our deep dive today, we're really focusing on those first 2 aims, creating new fluids and getting the data for those simulators.
Sounds good.
And the chapter really emphasizes water BIPA systems using GAR or its derivatives.
Why is that? Well, as they highlight in the chapter, water-based fluids using GAR or modified GAR polymers are really the workhorses of the industry.
Okay, so before we get into all the complex lab techniques, it sounds like there are some really basic but really critical steps. The chapter stresses starting with representative samples of everything. Water, hydrocarbons, even acid. But it specifically says getting a good sample of proppants can be tricky.
Oh, absolutely. It's a fascinating challenge to get a truly representative sample of those little proppant particles. They come in different sizes and densities. They tend to separate during transport and handling. Imagine you have a cereal box with different size flakes. The smaller ones, they settle at the bottom.
Of course,
Getting a sample that reflects the whole batch. That's surprisingly difficult, but essential for testing.
You need to know what you're working with, right?
Exactly.
And it's not just the materials, is it?
Nope.
The chapter talks about the lab environment.
Oh, absolutely. Calibrated, well-maintained lab instruments are non-negotiable. You know, if your equipment's not accurate, the data won't be either.
Makes sense.
And adhering to those standardized testing methods is so crucial. You know, things like those developed by API and SPE. That ensures results from different labs can be compared. Everyone's operating with the same fundamental understanding.
It's like speaking the same language.
Exactly.
And then it sounds like good old-fashioned record keeping is key.
You got it. The chapter really emphasizes keeping meticulous records of everything. Material samples, calibration data for the instruments, specific test conditions.
Wow.
This data can be used for years. You know, comparing different products, troubleshooting issues. It's the foundation of dependable science and engineering.
Okay, so we've got our representative samples, our accurate equipment, and our detailed records.
Check, check, and check.
Now, how do you even begin to replicate something as large and as complex as a fracturing treatment in a relatively small lab setting?
That's a great question, and it's important to remember. It's practically impossible to perfectly recreate the sheer scale and all the diverse conditions of a real fracturing treatment in one single lab experiment.
So it's just too big.
Right. So what scientists and engineers do is they break it down into a series of smaller, more focused tests. Each test simulating a specific critical aspect of the real-world environment.
So it's like a bunch of mini simulations?
Yeah.
Each one zooming in on a different part of the process?
And the scope of these tests can range from examining the behavior of individual molecules all the way up to testing fluids in large-scale equipment that starts to approximate the size of actual mixing tanks, well bores, and the fractures themselves.
And I'm guessing the specific tests you need to perform probably depend on the type of fluid you're working with.
Oh, the chapter mentions the oil-based fluids. Emulsions and foams might have different considerations.
Like what?
Well, you know, things like how much they compress under pressure or the size of the bubbles or droplets within them. Those properties are significantly affected by pressure. So you'd want to run tests specifically designed to see how they change across a range of pressures.
Now let's zoom in on those GAR-based gelling agents. The chapter talks about molecular characterization. What kind of techniques are used to really get down to that level?
It's pretty amazing the sophisticated techniques they use to understand these gelling agents. Things like intrinsic viscosity measurements, dynamic light scattering, NMR, SEC, and even a technique called freeze fracture electron microscopy.
Wow, that's a mouthful.
It is.
So what kind of information did these techniques actually reveal about the GAR?
It's a wealth of information.
Like what?
They help determine the size and shape of the GAR molecules. How they cross-link to form gels, the mechanisms by which they degrade under specific conditions, and even the structure of the gel network itself.
So you're really getting down to the nitty-gritty?
We are.
And before you even start formulating a complete fracturing fluid, it sounds like it's a good idea to analyze the raw GAR polymer itself.
Oh, it is.
Why is that so important?
GAR is a natural product. And like any natural material, it can vary from batch to batch. Suppliers do blend to try to ensure consistent quality for oil field applications. But it's still wise to analyze that base polymer. You want a clear understanding of your starting material before you start developing a new fluid system.
So let's talk about how the size of these GAR molecules relates to how thick the fluid becomes. The chapter discusses this connection between molecular weight and viscosity. And it mentions that GAR acts like a random coil polymer in dilute solutions. What does that even mean?
Oh, think of it like a bowl of cooked spaghetti.
Okay.
The strands are all tangled up randomly.
Okay, I can picture that.
That's a rough analogy for how these GOR polymer chains behave in a solution when they're not too concentrated. And just like a bowl with longer spaghetti strands will be more viscous and harder to stir.
Yeah.
The GOR solution's viscosity is directly related to the molecular weight of the polymer chain.
So longer chains, thicker fluid.
Exactly.
The chapter then introduces this concept of intrinsic viscosity. What is that and how is it measured?
So intrinsic viscosity is essentially a measure of the size or the volume of individual polymer coils in a solution.
Okay.
Think of it as how much space each polymer molecule occupies and how much it contributes to the solution's overall viscosity.
Okay.
Experimentally, you measure the viscosity of a series of very dilute solutions at low shear rates and extrapolate back to a concentration of 0. That extrapolated value gives you the intrinsic viscosity.
Interesting. And from there, we get this Mark-Howink equation.
Yes, we do.
It sounds very technical.
It does.
But what does it tell us practically?
It provides a really useful mathematical relationship between that intrinsic viscosity and the molecular weight of the polymer.
Okay.
It's I equals K times MV to the A,
right.
where K and A are constants determined experimentally for a specific polymer and solvent at a given temperature.
Okay.
And PIV is the viscosity average molecular weight. And what's really interesting is that exponent of GUD gives us clues about the shape of the polymer chain in the solution.
Oh, okay. How so?
For compact spherical molecules, it is close to 0. For long, rigid, rod-like molecules, it's around 2.
Okay.
And for those random coils like GUARD, it's typically between 0.72 and 0.8.
So it links the microscopic structure to something you can actually measure.
It does.
So we've got an understanding of how these individual chains behave. But what happens when you increase the concentration of GAR in the solution?
Yeah, that's where things get really interesting.
The chapter talks about a critical overlap concentration, or C-star.
Right.
Why is that so important?
As you add more GAR to that solution, those individual coils start bumping into each other and interacting. That concentration where this begins is the critical overlap concentration, or C-star. Really important, especially when we talk about cross-linking.
Why is C-star so critical for that?
Because below this concentration, those molecules are too far apart to form those connections between them, those intermolecular crosslinks.
Okay.
If you add a crosslinker when the concentration is below C-star, you mostly get crosslinks within the chains themselves, which doesn't create that strong gel network that you need for an effective fluid.
So you need those crosslinks to form between the chains.
Exactly.
And how do you determine this C-star in the lab?
Well, the chapter mentions the Kramer method.
Okay.
You measure the viscosity of the GAR solution at different concentrations, plot the logarithm of specific viscosity against the logarithm of the polymer concentration.
Okay.
And C-stars indicated by a noticeable change in the slope.
Interesting. The chapter gives a rule of thumb for polysaccharides, like GAR, saying C-star is roughly 4 divided by the intrinsic viscosity. Then it gives an example for a high molecular weight GAR used in fracturing, saying C-star is around 0.21 deciliters per gram, which translates to about 15 to 20 pounds per 1,000 gallons.
Right.
Is that a coincidence?
It's not a coincidence at all.
Oh.
What's really insightful is that C-star value falls right within the typical range of GAR concentrations used in cross-linked fluids.
Really?
15 to 20 pounds per 1,000 gallons.
So this molecular level understanding is directly informing the real-world application.
Exactly.
Now, the chapter also touches on measuring the distribution of molecular weights using size exclusion chromatography, or SEC.
Right.
Why is it important to know not just the average molecular weight, but also the range of molecular weights?
Think of it like this. You could have 2 different GAR samples with the same average molecular weight. One sample might have chains that are all very similar in length, while the other might have a much wider range with some very short chains and some very long ones. This distribution impacts how the polymer behaves.
How so?
Especially when it comes to how it crosslinks. Or how it degrades over time. SEC lets you see that whole spectrum of molecular weights present in the sample.
And this isn't just some academic exercise, is it?
No, it's not.
This actually has real-world implications.
Oh, absolutely. Like knowing the range of chain lengths, not just the average, tells us how uniformly the GAR will perform. And how susceptible it might be to degradation.
So you're saying that's a crucial factor for long-term, well, productivity.
Exactly.
And the chapter mentions that SEC is particularly useful for studying polymer degradation, even in samples that come back from actual fracturing treatments.
Right, those flowback samples.
Yeah, why is that helpful?
Analyzing the molecular weight distribution of the GAR in those samples gives you insights into how it's broken down during the process, which helps understand how effective the chemical breakers added to the fluid are under real field conditions.
Makes sense.
And knowing both the molecular weight distribution and the concentration of polymer in the flowback allows engineers to better predict its viscosity.
Right.
Which is important for managing its handling and disposal, and can even help estimate the risk of viscous fingering.
Viscous fingering? What's that?
It's a phenomenon that can hinder the well cleanup.
Okay, so we've talked about the water-soluble parts of GAR.
Yeah.
But the chapter points out that not all of it dissolves.
Right.
And these insoluble bits can either be present from the start or form as the polymer degrades. Why are these a concern?
They can definitely have a negative impact. They can contribute to fluid loss into the surrounding formation.
So less fluid available to create and prop open the fracture?
Exactly. They can also potentially damage the conductivity of that proppant pack,
meaning
essentially clogging up the pathways for oil and gas flow.
So how do you even analyze something that doesn't dissolve?
It's a challenge. But techniques like elemental analysis, looking at percentages of elements like carbon, hydrogen, nitrogen, and things like FTIR, Fourier transform infrared spectroscopy, can give clues about the composition. For GARO specifically, these methods can even give information on how the ratio of sugar units like galactose and mannose changes.
Interesting. Okay, let's move on to something that sounds really critical. Cross-linking. The chapter explains that cross-linking dramatically enhances the fluid's performance.
It does.
How does it achieve that?
Cross-linking creates chemical bonds that link those individual polymer chains together, forming a larger three-dimensional network structure. Think of it like going from individual threads to a big interconnected web. This network gives the fluid its high viscosity and the ability to suspend and carry those proppant particles.
And it does that at relatively low polymer concentrations.
That's important from an economic standpoint. And also to minimize damage to the fracture's ability to conduct fluids after the treatment.
The chapter then gets into the chemistry of cross-linking, specifically mentioning borate cross-linking. And how NMR has been used to study it. What's interesting about borate cross-linking?
Well, it's a very common and extensively studied system. What's neat is that NMR lets scientists see and measure the different chemical species involved. So you can actually see what's happening at the molecular level?
In a way, yes.
Okay.
It helps them determine the optimal ratios of borate to GAR.
Okay.
And even calculate the equilibrium constants for the reactions.
And that's important for controlling how the gel forms and how stable it is downhole.
Absolutely.
And the chapter highlights that the concentration of active cross-link sites in borate systems is really sensitive to both pH and temperature.
Yeah, it's incredibly sensitive.
How much so?
The concentration can change by more than tenfold just by shifting the pH from 7 to 9.2.
Wow.
Temperature also plays a huge role.
As temperature rises, the equilibrium shifts and cross-link concentration decreases.
So it's a bit like a recipe where everything has to be just right.
It is a bit like that.
So understanding these chemical reactions is really important for designing fluids that will work downhole.
Absolutely. By carefully choosing the components and controlling factors like borate concentration and pH. Engineers can design fluids that maintain their viscosity even at high temperatures.
Interesting. Let's shift gears a bit and talk about how these fluids actually flow. The chapter gets into rheology. And talks about measuring apparent viscosity. So what is apparent viscosity and why is it so important?
Apparent viscosity basically measures a fluid's resistance to flow under a specific shear rate.
And shear rate is?
Shear rate describes how quickly different layers of fluid are moving relative to each other.
Got it. So for simple fluids like water, the viscosity is constant. But most fracturing fluids are non-Newtonian,
Meaning their viscosity changes depending on the shear they're experiencing.
And this is critical because?
Because the shear rates in a fracturing treatment vary dramatically.
Like how?
Well, you have high shear rates when it's pumped down the well bore. And then lower shear rates once it's inside the fracture.
And how is apparent viscosity usually measured?
Well, the most common instruments are things like rotational concentric cylinder viscometers,
Okay.
capillary viscometers, and larger scale pipe or slot flow devices.
And I'm guessing each type has its own advantages.
Exactly. Each one's good for measuring viscosity under different shear rates and for simulating different flow conditions.
Okay, and then all of this data feeds into those mathematical models, right?
Yes, it does.
The chapter mentions the power law model as one of the most common ones.
It is.
What's the basic idea behind that?
The power law model is a relatively simple way to describe the flow behavior over a specific range of shear rates.
Okay.
It links the shear stress, the force that causes the fluid to flow, to the shear rate through two parameters.
Okay.
The consistency index, or K, which is a measure of the fluid's thickness, and the flow behavior index, or N, which indicates how non-Newtonian it is.
So for Newtonian fluid, N would be 1.
You got it.
But for most fracturing fluids, it's less than 1.
Right.
And that means they exhibit shear thinning behavior.
Exactly. As shear rate increases, the viscosity decreases.
Okay, so like if you're stirring paint,
yeah,
some paints are thick no matter how fast you stir.
Those are like Newtonian fluids.
Right.
Others thin out as you stir faster.
Yeah, that's shear thinning.
Exactly.
Yeah.
And the power law helps describe how much thinner they get at different stirring speeds.
So how do you actually get these K and N values in the lab?
You conduct viscosity measurements at different shear rates.
Okay.
And then you plot those points on a log-log graph of shear stress versus shear rate. And over that range where the power law applies, you'll see a straight line.
Okay.
The slope is N.
Okay.
And the shear stress at a shear rate of 1 gives you K.
But the chapter says the power law has some limitations.
It does.
What are those?
Well, it doesn't accurately capture the behavior at very low and very high shear rates. In reality, many fluids will become Newtonian at those extremes.
Meaning?
Their viscosity becomes constant.
Okay.
The power law can overestimate the viscosity at low shear rates.
And that matters because...
That can be an issue when considering how easy the fluid is to clean up.
From the proppant pack.
Yes.
So are there other models that give a more complete picture?
Yes, there are. The chapter mentions the Ellis model.
Okay, and how does that improve on the power law?
It incorporates a zero shear viscosity term.
Okay.
Often denoted as euro.
Okay.
So it better predicts that constant viscosity at very low shear rates.
Right, so it gives a more accurate representation.
Yes.
Across a wider range of conditions.
Right.
Now, fracturing isn't static.
Nope.
The fluid goes through a lot of changes in shear rate and temperature as it's pumped down whole.
Yeah.
How is this taken into account in the lab?
That's a really important point.
Yeah.
The fluid's properties downhole aren't just determined by its chemical formulation. They're also influenced by the entire history of shear and temperature it's gone through.
So from the moment it's mixed at the surface.
Exactly. Think about it. High shear rates down the wellbore.
Right.
And then much lower shear rates in the fracture.
Okay.
But the temperature is increasing as it heats up to the surrounding rock.
So you're saying to understand how it really behaves down there, you need to simulate those changing conditions.
Exactly. Researchers have these sophisticated testing protocols.
Okay.
And specialized equipment to mimic these shear and temperature profiles. This can involve subjecting the fluid to high shear, followed by low shear.
Okay.
All while increasing the temperature and monitoring its properties.
And are there standardized procedures for this?
Yes. API has developed recommended standard testing procedures.
And why is that important?
So you can compare data from different labs.
And how does applying shear actually affect the rheology of these cross-linked fluids?
Yes. Shear can have different effects.
The chapter separates reversible gels, like those cross-linked with borate and irreversible gels?
Like those cross-linked with titanate or zirconate.
Okay, let's start with the reversible gels. How does shear affect them?
At high polymer concentrations, well above that C-star.
Yeah.
Shear might have a minor temporary impact on viscosity.
Okay.
But at lower concentrations near C-star, high shear rates can destabilize the gel structure.
Okay.
It can separate into regions with high and low polymer concentrations. This shear-induced phase separation can cause a significant drop in viscosity.
But the crosslinks can reform if the shear is removed.
Exactly, because it's a reversible system.
And for those irreversible gels, the titanate or zirconate ones, how does shear affect them?
Applying shear during the cross-linking process
can
break down the network into smaller fragments. This permanently changes the fluid's properties and reduces its viscosity.
Okay.
So they use delayed cross-linking systems.
What are those?
They prevent the gel from forming too early.
While it's being pumped down the well bore.
Exactly.
But even in the lower shear environment of the fracture,
Yeah.
the shear rate can still affect the final viscosity.
Right.
Okay, let's not forget foams and emulsions.
Mm-hmm.
The chapter talks about their unique rheology.
It does.
What are the key factors there?
Well, the viscosity of foams and emulsions is influenced by several things.
Okay, like what?
The volume fraction of gas in foams or liquid in emulsions dispersed in the liquid phase.
Okay.
Also the size and uniformity of the bubbles or droplets.
Right.
The interfacial tension between those phases. And the properties of the continuous liquid itself.
So you're saying it's more complex than single-phase fluids?
It is. You have those additional factors to consider.
And characterizing them sounds even more challenging.
It is when you're characterizing foams and emulsions.
Yeah.
You need to measure the rheological properties, but you also need to report the volume fraction of the internal phase.
Okay.
The bubble or droplet size distribution.
Right.
And the interfacial tension. Unfortunately, a lot of earlier research didn't always include this detail.
So it's hard to compare.
Exactly. And phenomena like wall slip.
Wall slip.
Where the foam slips along the wall of the instrument.
Okay.
That can complicate things.
So careful equipment selection is important.
It is. You want to ensure the dispersed phase is small compared to the measurement boundaries.
Right.
Things like high-pressure circulating viscometers or single-pass pipe viscometers are often used.
And then there are more complex models like the volume equalized power law.
Right, or VEPL.
What's that for?
It tries to make viscosity predictions that aren't as dependent on the instrument's geometry.
And what about cross-linked foams?
For those, you need to test under conditions that reflect their use.
So higher proppant concentrations and temperatures.
Exactly. They also use empirical correlations, which based on data, not theory.
Okay.
To predict viscosity based on things like temperature and quality.
And it's worth noting that cross-linking the continuous phase can significantly increase the viscosity compared to a non-cross-linked gel.
It can.
The chapter also mentions how the geometry of the viscometer itself can influence the results.
Yes, it can.
And especially for these non-Newtonian fluids. Why is that?
The physical dimensions,
okay,
like the gap between the cylinders in a concentric cylinder viscometer, can affect the shear rate uniformity.
Okay.
Narrower gaps usually give a more uniform shear field. And using a volume average shear rate can help make the data less dependent on the specific geometry.
Okay, so moving beyond steady shear measurements. The chapter introduces dynamic oscillatory measurements.
Right.
What do those tell us that steady shear doesn't?
They reveal information about the fluid's microstructure and viscoelastic properties.
Okay.
Things you can't see with steady shear.
So what are you actually measuring in those tests?
Things like the elastic storage modulus G prime.
Okay.
And the viscous loss modulus G double prime.
And what do those represent?
G prime reflects the elastic behavior.
Okay.
The ability to store energy and recover.
Okay.
And G double prime reflects the viscous behavior.
How much it resists flow.
Right.
Okay.
And these are often more sensitive to subtle changes in the polymer network, polymer hydration or cross-link density.
Interesting.
You could have two fluids with the same steady shear viscosity, with very different G prime and G double prime values.
Showing they have different structures.
Exactly.
Right.
Dynamic measurements can also give insights into the cross-linking process.
Okay.
And how elasticity helps suspend those proppant particles.
So G prime is like how much the fluid acts like a spring.
Yes.
And G double prime is how much it acts like a thick liquid.
Exactly.
And these dynamic measurements can also give information about the fluid's relaxation time.
They can.
And whether it might slip at the boundaries, right?
That's right. Okay, so what is relaxation time? It's the time it takes for the fluid structure to relax after being deformed. And it's often represented by lambda.
Okay.
Then there's the Deborah number, which compares this relaxation time to the flow time.
And what does that tell us?
If it's greater than 1 Wenank, the fluid's elastic behavior dominates.
Yeah.
And it might slip at the interfaces.
Leading to inaccurate readings.
Right.
So you need to use multiple geometries to distinguish between real viscosity and slip effects.
Exactly.
Now let's talk about proppant slurries.
Okay.
The chapter mentions that their rheology is often more complex and less well understood.
Right.
Why is that?
When you add those solid particles to the fluid, it adds a whole new layer of complexity.
Okay.
The rheology now depends on the fluid's properties,
right,
but also on the proppant itself. Its size, shape, density, concentration. The flow conditions the temperature.
Okay, so anyone who's tried to really get into the nitty-gritty of how we figure out what's happening miles underground knows it can get pretty dense, right?
Yeah.
But that's why we're here, to make this stuff actually make sense and connect the dots.
Exactly.
Today, we're going deep on using pressure, like pressure changes, to understand fractures.
Specifically during hydraulic fracturing, right?
Yeah.
Which is, creating those fractures to get oil and gas flowing.
It's wild to think we can actually learn so much from just watching how the pressure goes up and down.
Yeah, pressure's like the language of these fractures,
All right.
It's how they kind of talk to us.
So the source material we're diving into today is a chapter that's all about this. It's like a detective manual for decoding those pressure signals.
It is. And it's super insightful.
Okay, so imagine you're trying to actually see these cracks.
Miles down.
Miles down, yeah.
Good luck.
It's almost impossible. I mean, there are some techniques, right? Like they put radioactive tracers in the fluid, or they use these tilt meters that can sense tiny ground movements, or they even listen for these micro earthquakes with microseismic sensors.
Right.
But our source is quick to point out these methods. They have their limits.
Yeah, they do.
They might only give you like a snapshot after the fracturing's done, or they only show you part of the picture, or it's like insanely expensive to do some of that stuff.
Yeah.
So that's where the pressure diagnostics, that's where it gets really interesting.
It does. It really does.
It's like instead of trying to directly see the cracks, we're listening to them. We're feeling their pulse through the pressure changes.
Exactly.
So we're measuring that pressure downhole, like right at the bottom of the well.
The whole time, yeah.
The whole time during the whole process.
From the moment we start pumping that fluid, right through to when we shut everything in and the fracture starts to close.
Right. So you've got that initial pumping phase, then the shut-in period, then the eventual closure. And our material really emphasizes that each phase of this pressure story, each one is like a clue.
Yeah.
It tells us something different about the fracture.
Absolutely. And they all work together. Right?
Yeah. And there's this key step they talk about called a calibration treatment.
Oh, yeah, the mini frac.
The mini frac, yeah.
Right.
So it's like a practice run before the main fracturing job.
A test drive.
A test drive, yeah.
Exactly.
But they do it without the proppant.
Right.
The sand or ceramic stuff they pump in to hold those fractures open.
Keeps them propped open.
Keeps them propped. But they don't use that for this calibration treatment. And what they're looking at is the pressure response during that mini frac.
And that gives us a really good baseline.
Yeah. It tells us so much about how the rock's going to behave.
Exactly. It's all about understanding the formation before we go full scale.
Okay, so the whole idea of pressure analysis, it rests on like 3 fundamental principles, right?
Yeah, think of them as our guiding stars.
Okay, yeah.
The first one is material balance.
Okay.
Which is basically accounting for everything that goes in and out.
So like a ledger, an inventory.
Exactly.
Okay.
Then we've got fluid flow, how those fluids are moving within the fracture itself.
Okay.
And last but not least, we have to think about the rock, how it responds to all this pressure.
Yeah. Yeah. The rock itself is changing.
It's changing shape, yeah.
Okay.
So that's where rock mechanics comes in.
Right.
It's all connected.
So this material balance, that's all about knowing exactly how much fluid we're pumping down there and then watching what happens when we pump it in and when it starts to, come back out.
Exactly. We're looking at the volumes.
Yeah.
How much is going into actually creating those fractures and how much is leaking off into the surrounding rock.
Okay, right. So you're distinguishing between the fluid that's actually making the fracture versus the fluid that's just seeping away.
Exactly.
Okay, and then you've got the fluid flow.
Yeah. So here we're getting into the nitty-gritty of the fluid itself.
Okay, yeah.
How thick it is, how fast it's moving, and how wide the fracture is. All of these things affect the pressure.
Right.
We need to push that fluid along.
So it's like a thicker fluid's going to need more oomph to get it moving.
Exactly.
Yeah, exactly.
Okay. And then this connects directly to that third principle, the rock mechanics.
Right. So as that fluid is being pushed, it's creating pressure inside the fracture.
Okay.
And that pressure is pushing outward against the rock.
Right.
Causing it to deform, to change shape, and the fracture to actually widen.
So it's like, it's a dance, right?
It is.
Between the fluid pushing and the rock giving a little...
Yes, delicate balance.
Okay. And out of this whole dance between pressure and deformation comes this super important concept of closure pressure.
Yeah, that's a big one. Our source material calls it the baseline pressure for how a fracture behaves. Can you break that down for us?
Sure. So imagine the Earth is always trying to squeeze that fracture shut.
Right. Okay.
Closure pressure is that point where the Earth's natural forces are finally strong enough to do just that.
So it's like a battle, almost.
It is a battle.
Okay.
Between that pressure we're putting on it and the Earth pushing back.
Right, right.
And it's very closely tied to this thing called the minimum horizontal stress.
Okay.
It's like the baseline stress that's always present in the rock.
So that's like the squeeze that's already there even before we start fracturing.
Exactly. And there's a good diagram in the book, figure 9:1, that shows this.
Okay.
It shows how the net pressure inside the fracture, that's basically the difference between the total pressure and this closure pressure.
Okay.
So closure pressure, it's like this threshold.
Right.
We need to overcome that to even create a fracture and keep it open.
Okay, that makes sense. But the material also throws in a little bit of complexity.
Of course they do.
Right. Sidebar 9A in our source mentions that this closure pressure, it's not always a nice single number.
Right.
It can depend on the shape of the fracture and even vary across the reservoir.
It can, and that's because rock formations aren't perfectly uniform.
Right.
Like you might have different types of rock present.
Okay.
There could be natural cracks or weaknesses too.
Okay, yeah. So it's not like a perfectly smooth block.
No, not at all.
It's got all these variations.
Exactly, and all these variations affect the stress.
Right.
So a small, shallow fracture might experience a different pressure than a large, deep one.
Right, because it's feeling the squeeze from a smaller area of rock, maybe.
Exactly.
Okay, and it's interesting that this whole idea of injection pressure being important, it's not new.
Oh, it's been around for a while.
Our source says it goes all the way back to the 1950s.
Yeah, back when they were just starting to figure out this whole fracturing thing.
Right, but it sounds like things really picked up steam again in the mid-1970s.
They did.
What happened then?
Well, a few things. For one, government regulations on gas prices started to loosen up.
Okay.
So suddenly, some gas reservoirs that had been uneconomical before started to look a lot more attractive.
Right, because they could actually make money from them now.
Exactly. And then there were some huge oil discoveries in other parts of the world.
Okay.
Which actually slowed down fracturing activity in some areas initially.
Oh, interesting.
Yeah. But then the industry kind of pivoted.
Okay.
And they started using much larger hydraulic fracturing treatments.
Right. So instead of just giving up on fracturing, they went big.
They went huge.
Okay.
Enormous quantities of fluid and proppant.
Right. And all of a sudden, the cost of these treatments went way up.
Way up. And it became crucial to make sure those treatments were successful.
Right, because you're putting a lot more money down.
Yeah. So the stakes were higher.
Okay.
And that really pushed a renewed focus on pressure.
Right, because you got to squeeze every bit of value out of those expensive treatments. Okay, and so since the 1980s, analyzing pressure has become a pretty standard tool.
Oh, yeah.
Not just for regular fracturing jobs, but for those more specialized, complex ones too, right?
It is.
Like it's become part of the toolkit.
Absolutely. And researchers have developed all these different variations of that basic calibration test.
Okay.
For specific purposes, you know.
So it's like the basic test, but then they've got different spins on it.
Exactly. So like we've got step rate and flowback tests.
Okay.
Those help us really pinpoint that closure pressure.
Okay, so it's all about getting more precise.
Mm-hmm. Then there are step-down tests to identify problems near the wellbore.
Okay.
And even just short injection tests can give us clues about the reservoir's permeability.
Okay. So there's a whole suite of pressure tests now.
The whole suite.
Okay, so let's dig a little deeper into those core principles we were talking about before.
Okay, yeah.
So with that fluid flow, how the fluid moves within the fracture.
Mm-hmm.
Our source mentions something called a power law model to describe the rheology.
Which is just a fancy word for flow behavior.
Okay, flow behavior.
Yeah. And it's basically how these fracturing fluids, which are often really complex, by the way,
okay,
how they behave under pressure.
Okay, so the power law model is trying to capture that complexity.
It is. And it uses these parameters we call K and N.
Okay.
Don't worry too much about the details there.
Right.
What's important is that for most of our operations, the flow inside the fracture is laminar.
Laminar, okay.
Which means it's nice and smooth.
Okay, so not turbulent.
No, not turbulent, no. Think of it like layers of fluid flowing past each other without much mixing.
Okay, so kind of like a layered cake, maybe?
Yeah, kind of.
Okay.
And then there's an equation in our source, equation 9:2.
Okay.
It's a way to relate the pressure we need to the injection rate and the fracture dimensions.
Okay.
Taking into account this whole power law behavior.
Right, so it's like a formula that takes all those factors into consideration.
Exactly. It helps us predict how much pressure we'll need at the surface to achieve the desired flow rate downhole.
Okay, so it's a predictive tool.
Mm-hmm.
Okay, and then we've got material balance.
Right, our ledger.
Measure.
Yeah, our inventory.
So to make things a little simpler, our source is kind of ignoring the fact that some fluids can compress a little bit?
Yeah, they're focusing on volume balance.
Volume balance, okay.
Which, for most cases, it's a pretty good approximation.
Okay.
So what are the key things to remember here?
Yeah, what do we need to know?
First, there's equation 9-4.
Okay.
It defines treatment efficiency.
Which is?
It's basically how much of the fluid we pump in actually goes towards making the fracture bigger.
Okay.
Versus how much leaks off into the rock.
Right.
Then there's equation 9-5, which tells us the total volume injected is the sum of the fracture volume and the volume that's leaked off.
Okay.
And finally, equation 9-7 helps us estimate the fracture volume during that shut-in period, while that fluid's still leaking away.
Right. And the source has a really helpful figure 9-2.
Oh yeah, that one's good.
That shows these volume relationships visually.
It does. It makes it a lot clearer.
Yeah, so you can see how much is staying in the fracture, how much is leaking off.
Exactly.
Okay. Now, let's talk about the rock itself.
Okay.
How it deforms, how it changes shape when we're pumping all that fluid in.
Right. So our source mentions that we typically assume linear elastic deformation.
Okay, and why is that?
Well, it's a reasonable assumption for a couple of reasons.
Okay.
Firstly, the fractures we're creating, they're still pretty small compared to the huge natural stresses that already exist deep down.
Okay.
So we're not talking about massive earth-shattering changes here.
Right, it's like poking a small hole in like a giant sponge.
Yeah, kind of.
Okay.
And for the most part, the rock responds to that pressure in a predictable way.
Okay.
Linearly elastic, meaning if you double the pressure, you've roughly double the deformation. So it's a proportional relationship.
Right. It's like stretching a rubber band.
Exactly. And our source gives us two really fundamental equations for cracks in an elastic material.
Right.
One for a long, flat crack, kind of like a sheet of paper.
Okay.
And another for a circular or penny-shaped crack.
Okay.
And figure 9-3 shows these really nicely.
Okay.
These equations relate the width of the crack to the net pressure inside it and the elastic properties of the surrounding rock.
Okay.
They're like the building blocks for understanding how these cracks behave.
So they're telling us how wide that crack is going to get based on the pressure and the rock type.
Exactly.
Okay. And these equations, they're the basis for those two main fracture models that we talk about, KGD and PKN.
Yeah, those are our go-to models.
Okay.
And they come straight from those 2D crack equations we just talked about.
Right. So what are the big differences between those two models?
Well, the KGD model is named after a few guys.
Yeah.
Kristjanovich and Zheltov first, then Giertzma and de Klerk refined it. But anyway, KGD, it works best when the height of the fracture is much bigger than its length.
So like a tall, skinny crack?
Exactly.
Okay.
PKN, on the other hand, which comes from Perkins and Kern and Nordgren,
Okay.
that one assumes the length of the fracture is dominant.
So like a long, wide crack.
Right. So as a rule of thumb, KGD is good when the length is less than about 1/3 of the height.
Okay.
And PKN is better when the length is much greater than the height.
Okay, so they kind of cover the two extremes.
Yeah. And then we've got the radial model.
Right.
That one's best when the length and height are roughly equal.
Okay, so like when the fracture's growing outwards in a circle.
Exactly.
Okay, cool. Our source also talks about fracture compliance.
Right. Another key concept.
Yeah, it's defined as the relationship between the average width of the fracture and the net pressure.
At the well bore.
At the well bore, right.
And it's a direct relationship.
Okay.
You can see it in equation 921.
All right, and why is compliance so useful to think about?
Well, it tells us how stiff or flexible the formation is.
Okay.
In response to the pressure we're applying.
Okay.
Our source compares it to how fluids behave in a reservoir.
Okay.
Some fluids are more compressible than others.
Right, yeah.
Same idea here. Some rock formations are more compliant than others.
So some will open up more easily, you mean?
Exactly. And the compliance, we denote it as CF.
Okay.
It depends on the rock properties, a geometric factor, and which 2D fracture model we're using.
Okay.
But basically, it tells us how much the fracture will open up for a given pressure increase.
Okay, so it's a measure of how much the rock is willing to give.
Yeah, it's give or springiness, you could say.
Okay. That makes sense. So now when we're actively injecting fluid,
it
seems like the pressure isn't really that sensitive to how efficient our fracturing job is.
You're right, it's not.
Like how much fluid is being lost to the formation doesn't seem to affect the pressure that much.
It doesn't, and you can see that in equations 930 and 931. Even if our fluid efficiency varies quite a bit, meaning how much stays in the fracture versus leaks off, the net pressure during injection doesn't change that dramatically.
Okay, so we can't just rely on watching the pressure gauge while we're pumping to know how much fluid we're losing.
Right.
Okay, but figure 9 to 5 in our material shows an interesting idea.
Yeah, the idea of scaled time.
Okay, what's that?
Well, we could approximate the net pressure with fluid loss by looking at a scenario with no fluid loss.
Okay.
But we have to adjust the time scale.
Right. So it's like we're compressing the time to account for that lost fluid.
Exactly.
Exactly.
Okay, and then our source gives us some equations for, like, boundaries for how far the fracture might grow and what the net pressure might be. And they specifically point out that these are power law relationships.
Which is important because if we plot the net pressure versus time on a log-log scale, we should see a straight line. And this is called a Nolte-Smith plot.
Nolte-Smith, yeah. And the slope of that line tells us something about the shape of the fracture.
Okay, so it's giving us visual clues about the geometry.
It is. So like a positive slope, that usually points to PKN-like behavior.
Okay, where length is the dominant dimension.
Right. Negative slopes often mean KGD, where height dominates. Or radial growth.
Right. And they compare this Nolte-Smith plot to those log plots we use in regular well testing.
Yeah, it's a key diagnostic tool.
So it's like its own special kind of fingerprint for the fracture.
Exactly.
Okay, now let's talk about fracture height.
Okay.
How tall those fractures grow. It seems like the difference in stress between the reservoir we're targeting and the layers above and below, that plays a big role.
A huge role. It's all about stress contrast.
Okay.
So if there's a big difference in the minimum horizontal stress between the reservoir and the adjacent layers, that acts like a barrier. It resists the fracture from growing upwards or downwards.
Okay, so it's like the rock is saying, nope, not going that way.
Exactly. But if that stress contrast is weak, the fracture can grow out of the zone we want.
Right. And figure 9 to 7 in our source, that shows some relationships between the net pressure and that stress difference.
Yeah, it helps us predict whether height growth will be contained or not.
Okay.
And it highlights a really important point. If your initial fracture height is small, it's more likely to grow vertically.
Oh, interesting. So starting small can actually be a problem.
It can be.
Okay. And they say that uncontrolled height growth can actually lead to the pressure decreasing, right?
Yeah.
They also mentioned something called a pinch point. What's that?
So a pinch point is often caused by a thin layer of rock that has much higher stress than the rock around it. And figure 912 shows how this pinch point can squeeze the fracture, making it narrower in that spot.
Okay. So it's like a bottleneck.
Exactly.
Right.
As long as the fracture is squeezing through that pinch point, the pressure might stay pretty stable. But once it breaks through, it can grow rapidly in height.
And that release of pressure, that causes the pressure to drop in the main reservoir.
It can, yeah.
Okay. And they have a field example of that in figure 913. Now, they also talk about these scenarios where you can get two-shaped fracture.
Yeah, where the fracture starts growing horizontally.
Yeah. When does that happen?
Well, it can happen in shallower formations where the weight of the rock above isn't as much. Or in areas with high pore pressure. Where the horizontal stresses are actually greater than the vertical stress.
Maybe
and figure 914 shows how the pressure responds to that T-shaped fracture. You get this kind of stable period as the fracture starts growing sideways.
So the pressure signature can tell us that's happening.
Exactly.
So they talk about net pressure capacity.
Right.
And how uncontrolled height growth can, like, exceed that capacity.
Yeah.
And they have some strategies to prevent that from happening, right?
Right. So if the pressure gets too high, because the fracture can't grow the way it wants to, that can cause all sorts of problems. Figure 917 shows how reducing the viscosity of the fracturing fluid can help manage that height growth. Basically by keeping the pressure down.
So you use a thinner fluid.
Yeah. And for cases where we're losing a lot of fluid into natural fractures or fissures, they talk about using very fine particles in the pad fluid, like 300 mesh material, to block those leak-off pathways.
Right from the start.
And then they also mention using larger particles like 100 mesh sand right before the prop end.
Okay.
To bridge those fissures.
Okay, so different size particles for different purposes.
Exactly. And these additives can even help control that excessive height growth, or those T-shaped fractures we talked about.
Okay, how?
Well, they bridge across those pinch points.
Oh, I see.
Like in figure 919. But, and this is a big but, the timing of when we inject these things is really important.
Right, because you don't want to clog up the fracture too soon.
Exactly. We don't want to screen out.
Right, so we've got to be really careful.
Very careful.
Okay, let's talk about screen outs.
All right.
So a screen out, that's when the fracture gets blocked with the proppant.
Yeah, our worst nightmare.
Right.
Well, one of them, anyway.
Yeah.
Because it stops everything.
Okay.
Right.
So what does a screen out look like in terms of the pressure?
Well, you'll see a very rapid increase in pressure.
Okay.
Because the pathway is getting restricted.
Okay, makes sense.
And figure 920 shows how the slope on that log plot, that net pressure versus time plot, it changes after a screen out.
Okay.
Equation 941 actually gives us an equation for that slope when we don't have much initial leak off.
Okay.
You know, that spurt loss.
Right.
And figure 922 shows some real-world examples of pressure behavior after screenouts in both low and high permeability reservoirs.
Okay. So again, different pressure signatures for different situations.
Exactly.
Okay. Our source then introduces this idea of the pressure derivative.
Oh, yeah. That's a good one.
What's the benefit of looking at that, how the pressure's changing over time versus just the pressure itself?
Well, the pressure derivative is basically mirroring that slope we see on the log-log plot.
Okay.
But it can be more sensitive to subtle changes.
Okay.
And it's also independent of the closure pressure.
Meaning?
Meaning, if we're a little off in our closure pressure estimate, it won't mess up our derivative analysis.
Okay, that's good.
It's a very robust tool.
Okay. And they say it can be really useful for, like, confirming the fracture geometry, validating our closure pressure, and spotting those screen outs.
Exactly.
Okay, now all of this has been pretty theoretical.
Right.
So our source gives us some real-world examples.
Of course they do.
Yeah, they talk about a reservoir with shale barriers and one with a radial fracture. What were some of the key takeaways from those examples?
Well, that shale barrier example.
Okay.
It showed how that log-log analysis could reveal a PKN-like fracture.
Okay.
Once the height growth got limited by those barriers.
Right.
And the radial fracture example, that one's in figures 910 and 911.
Okay.
It showed a log-log slope that matched the predictions for radial growth.
Okay, so it was behaving exactly as the theory predicted.
Exactly.
Okay, and now, sometimes things get a little messy.
Oh, yeah.
Near the wellbore?
Right. Near wellbore effect.
Near wellbore effect.
They can throw a wrench in the works.
Okay, what are some of the issues there?
Well, we can get pressure losses near the wellbore.